start now. Please take a seat. Okay, we start with the welcome by the director of the Observatory of Transients, Marcello Mattoni.
Good afternoon, welcome to everybody. I'm really happy to host this LSST Transients and Variable Stars workshop, both because here in Naples there are a number of colleagues that are really interested in LSST, and also because I think it is a unique opportunity for all the Italian community to get in touch with people that is really part of the LSST system and to understand how to optimize our contribution. So I wish you a fruitful time here, and thank you again for coming. And I think that.
So thank you for the Observatory of Capodimonte to invite us to have this beautiful, I hope, meeting. So we start immediately with Federica Bianco. And meanwhile, in the meantime, thanks a lot to everybody to be here. I hope that in this meeting we spend some time to discuss, to know each other, to discuss with our colleague in the USA. So, Federica, please.
Hello, can you hear me?
Yeah.
Louder. I'll try to be louder. I don't see my slides yet. Oh, yes, there it is. So actually, thank you very much for inviting me here. I'm really excited. This is the first time I speak in Italy about science since I graduated at Bologna University several years ago. So this is very exciting. I'm just going to give you a brief overview of LSST. I have a lot of slides, more than I can go through in 20 minutes. So just skip, and then if I skip something that you're interested in, stop me, and I'll go back. Oh, is that better? And I'll go back to the slides that you want to see. That's good. So let's begin by talking about LSST stands for Synoptic Survey Telescope, but really we don't talk a lot about the telescope. We talk mostly about the survey because that's more interesting, but just to give you a little bit of a recap about the telescope, it's actually a relatively small telescope, 6.7 meter effective aperture. Actually, it's 8 meters aperture. Field of view is 9.6 square degrees. That's a pretty stunning number. And it has a large, what we call entendu, which is the area by the collecting area by the field of view. So effectively, it means it has a large field of view, a very high resolution. But the survey is what interests us, and the survey is something that will happen between 2022 and 2032 for 10 years. During those 10 years, the telescope will perform what we call the wide, deep, fast survey. This is mostly what we talk about when we refer to the LSST survey, which will take something in the range of 75 to 95% of the sky time of the telescope. That number can change depending on how effective the survey is. The idea here is to take no compromises and do a survey that is all of wide, deep, and fast. So generally, we think there's a number of surveys that have tried to do 2 of these 3 things at a time, like TTF, which was wide and fast, but not very deep, etc. Supernova Legacy Survey, which is deep and fast, but not wide. LSST will do all 3, so covering a large swath of the sky down to a very faint magnitude in a short amount of time, which really effectively means repeating the observations at short time intervals, which is what we really care about if we think about transients. There are 4 science drivers of LSST: the study of dark energy and dark matter, the studying of the stellar structure of the Milky Way galaxies and its neighbors via result stellar population, an inventory of the solar system, which will include near-Earth asteroids, potentially hazardous objects, as well as the faraway Oort cloud and Kuiper belt, and then exploring the transients and variable star, which is probably what gets you the most excited for all the people in this room. But I want to point out that all of those science goals really actually have to do with the transient sky, because dark energy and dark matter exploration will largely happen through supernova, which is a transient phenomenon. Obviously, the transient and variable universe exploration is all about the transient sky, but the study of the stellar structure of the Milky Way and its neighbors by result stellar population will also interest transient transient experts and transients enthusiasts through the study of variables, eruptions, explosions, precursors of supernova and all that. And if you think about it, even the solar system, moving objects are transients. So how is LSST going to do that? First of all, it's going to do that from an awesome site where the sky is absolutely stunning. This is the Atacama Desert in Cerro Panchon in Chile, right here. And it's going to do a really crucial piece of the puzzle that I'm not going to talk about at length at all is the innovative optical design of the telescope. It's a design that allows you to have an 8.4 meter telescope in diameter, which is this chubby little object here that looks really quite funny, and which has an aperture that is comparatively small, but it's very different from all the other 8 meter class telescopes that we have currently. You know, you think about, for example, Gemini here at the top is also an 8 meter class telescope with a very different telescope design and obviously a very different goal and aim, which is going very deep in very small regions of the sky. LSST will cover an area that compares as such here on your right with the area of sky that covers that Gemini covers with a single image. So 9.6 square degrees down to a very faint magnitude. And you have the moon for comparison to give you an idea of what 9.6 square degrees are. A lot of this is achieved through the optical design, and a lot of this is achieved through the design of a really impressive instrument. The camera that LSST will have is a revolutionary instrument. Here you have a little video with a fake person on the side that gives you an idea of the size of this object. It's about the size of a Mini Cooper. This is how many iPhones it would take you to cover the plate field of the camera, 3.2 gigapixels. And then the thing that gets me the most excited is the data stream. So LSST will provide 20 terabytes of data, which will come at you at a rate of 30 gigabytes per minute. This is how many of my laptops it would take to take the data for one night and just store it, not to mention about processing it. Of course, storing is not what we want to do. We do want to process it. We want to process it quite fast, actually. And all of that will happen in the US, in Illinois. But the data is getting taken in Chile. So to transfer the data, actually, LSST has provided dedicated pipes to move the data from Chile to Florida, from Florida to Illinois, as well as with a redundant connection to Brazil. This is really important because this kind of data rate cannot be transferred through regular pipes, and this will enable particularly the exploration. This rapidity will enable the exploration of the transient sky. So again, the transient sky, LSST's data products. There's 3 classes of data products. I'm going to go through them one by one, but the one that you care the most at this time is what's called now the prompt data product. And you may have heard about it in the old way that we used to refer to it, the level 1 data product. That's now no longer the way we choose to refer to it, the prompt data products. This is a stream of 10 million time domain events per night. Let me say it again. Every night, LSST will look at the sky and will find about 10 million things that have changed. We'll find that by subtracting an image from a template image and noticing that something is different to a 5 sigma level, whether something appeared to a 5 sigma level or disappeared to a 5 sigma level. As well as a catalog of 6 million solar system bodies, which is also part of the data of the prompt data product data product. So this is the timeline. LSST takes 2 images. Each one is 15 seconds. There are 2 15 seconds images as opposed to 1 30-second image, largely to facilitate the cosmic ray removal. So that cosmic ray are not really a problem when you try to find the transients and don't constitute a significant source of false positives. Then the data gets transferred and the clock starts. And the LSST team, the LSST team project, has a goal of releasing these alerts in 60 seconds. This is a self-imposed timeline, and this is the way the LSST team likes to show it. These are your image pair that gets taken, and this is the image processing time that I like to show you with that Gantt chart. And I always show this movie at this point of the talk because I think it's a more realistic representation of what's going to happen. So we have this goal of, LSST has this goal of giving you all the transits, all the things that have changed in that portion of sky within 60 seconds of the image being taken. The second kind of data products that the LSST data management team will provide is a data with what we call the data release, which is the standard data release, which will happen every 6 months. This is your static sky, the new templates, the observation, the astrometry and photometry for all the static transients, things that you're interested in if you work on Milky Way, as well as if you work on extragalactic science. And the deep co-added images. So these are the data release that will allow you to get to a magnitude of 27 over time. There is one third set of data products which are not generated by the team, but they're generated by us, by the science people that work around LSST. So largely at this stage by the science collaborations. These are called the user-generated data products, and this is something that should interest you very much, and you should think very much about creating some of these. So these are things that the community writes because they're necessary for their science, but they're not integrated in the general data pipeline, the LSST data pipeline, that can be integrated and they can be run automatically if they get, so to speak, promoted for that to happen, and they can run on the LSST computational resources which LSST will provide to the community. The survey. So I'm not going to go into a lot of detail about the survey, but as I said, generally most of the time that we talk about the survey, we talk about the wide deep fast survey. This is basically your sort of, I don't know, Roman red here. That's the largest portion of the sky will be covered by the wide deep fast survey. That's the survey that sometimes you hear things like a movie of the sky with an image every 3 days or whatever it is. There's other surveys, there's other ways in which the LSST will observe the sky in those 10 years. Here you have a couple of mini surveys. So these are complementary to the wide, fast, deep. They're surveys that are proposed by the community and that cover areas of interest with a different cadence and a different strategy than the main survey. So for example, here you have the North Ecliptic Survey, the South Celestial Pole Survey, and the Galactic Plane Survey. And then there's these dots, which should be very interesting to you as a time domain astrophysics person. Those are the deep drilling fields, which are the fields that will be selected and will be observed at a faster cadence to go both deeper and collect images at shorter time intervals. All of these is in the planning. Because as you can imagine, there's many ways in which you can go and design a survey that does all that. And there's many ways that will encounter tensions between different goals. So the 10 years of the survey are designed to fulfill the 4 scientific goals, the 4 science drivers that I mentioned earlier. But sort of how well LSST will do certain things like supernova as opposed to transiting planets will depend on the very small details of that survey. And there are tensions such as, do you want to really emphasize the going fast and dense, or emphasize regularity and persistence in the observations? Do you want to emphasize the depth or the width or the breadth of the survey? Do you want to, for example, do more deep drilling fields but go a little bit shallower on them, or do fewer and go deeper? And also, as transient people, a very important tension, I think, which is between the shape of a transient and the color of a transient. If we only have 3 observations per night, or if we only have 2 observations per night, which is actually the most likely circumstance, do we want them in the same filter to get the shape of the transient, how fast it's rising or decaying, or do we want them in 2 different filters to actually get a reliable color? So all of those small differences and tensions are being investigated by the science community, and the science community is communicating them to the project to actually design an optimal survey. Here you have a representation of the LSST survey as it was simulated recently with sort of what's called the baseline cadence, which is the Minion 1016, that's the name of the cadence. It's here at the top. And here you see shifted how LSST compares to other surveys. Sorry, I should have said, this is filters, this is magnitudes, this is the 5 sigma depth per visit, this is the gap between images in a single filter, so a quantity of very much relevance for transient people, and this is the area in square degrees. So these are two different representations of this, two different possible realizations of the survey. One is the minion, the baseline cadence that has been simulated and we just sort of think of as the most likely cadence as it stands right now. And the one that is now in full color is the rolling cadence, a cadence that will work rather differently by going over the same fields faster at the beginning of the survey and slower later in the survey, and switching fields at which that it covers at different cadences. So a cadence that changes in each portion of the sky throughout the 10 years of the survey, which is very promising for transients, perhaps not as promising for science that requires regular observations. Okay. So the other little piece of overview that I want to give is the LSST ecosystem, sort of what I refer to as the LSST ecosystem, and there's an extra H here. There's a lot of confusion about what's LSST project, what's LSST corporation, what are the science collaborations, and what the relationship between those are. I will not fully clear this confusion, but just to give you an idea. So the LSST project is basically the people that are paid by the Department of Energy and NSF grants that originally sponsored LSST to develop, build, and create the strategy for LSST. These are the main players, Steve Kahn and Beth Willman as the director and the deputy director, etc. You probably interacted with Željko Juzevic, who's the project scientist, Anthony Townsend, and Victor Krabnam. There's more people that I have in the slides, and you can look at the slides later, and also obviously on the website. And then there is the LSST Corporation. The LSST Corporation is a non-profit that was founded in 2003 to basically seek funds outside of the NSF and DOE funds that are sponsoring the project to sponsor the community, to do the science that will be necessary to actually make the project a really successful project, particularly until the beginning of observations, but also continuing after that. The LSST Corporation continues to raise funds and enabling the sort of slogan that they use is enabling science. They have recently set up 2 new job positions that are just designed specifically to make contacts with foundations to help support the work of scientists that work outside of these NSF and DOE grants and that are trying to prepare for LSST. And so in this context, the science collaborations are related to the LSST Corporation, but they're not supervised or managed by the LSST Corporation. The LSST Corporation simply facilitates their work through facilitating communication. It gives you access to Slack that many of you love and many of you hate, and I force you all to use. And to community, the board where we can connect and have discussions online, which is kind of like a Stack Overflow-like board. These are the 8 science collaborations at present: Galaxy, Stars and Milky Way, Solar System, Dark Energy, Active Galactic Nuclei, Transients and Variable Stars, that's us, Strong Lensing, and Informatics and Statistics. The science collaborations were created in 2006, largely to write the LSST book, to understand what was the potential of LSST, and to propose LSST as a real important priority for the US astronomy in the following decade, and in fact it was confirmed to be such by the decadal survey. Since they were created by the project and at the time managed by the project, since then the project has stepped down, so they're now independent entities that are not managed by the project or by the corporation. They set their own publication policies, they set their own membership structure and hierarchical structure inside of them, etc. And they're still working to understand the LSST, how to develop the LSST survey, and this is the latest effort, the science-driven optimization of the LSST observing strategy, which was led by Phil Marshall and was published in August of last year, and it's a living document that continues to be worked on. I'm running late. So there's interplay between the 4 science drivers and the science collaborations. They were created so that there was a science collaboration for each one of those, but in fact there is a much more complex intricacy of interests and expertise. The science collaborations used to be, a membership to the science collaborations used to be unique, so you could only be a member of one science collaboration. This rule has been relaxed. Now you can be a member of many science collaborations, and in fact, if I go a few slides back, this diagram shows you the membership across the science collaboration. So each ribbon shows how many members of one science collaborations, for example, transients, also belong to statistics and informatics, etc. So it generates a potentially very interdisciplinary and interactive environment for science. You, as PI, as people that have signed, as organizations that have signed an MOU with the LSST Corporation, have access to the science collaborations. So the science collaboration on this way become international. Of course, everybody that is a data right holder, so everybody in the US community and Chilean community also has access to the science collaborations, and largely they've been dominated by US members, but we're very happy to see a lot of Europeans joining recently. And let's see. Let me just go briefly through the LSST timeline because I think this may be really of interest. So we are here in Q2 of F18, at the beginning of Q2 of F18. So we're on track for data management as roughly half the way through the release of the final data product pipeline. The telescope site is being prepared and things are being built. You probably have seen the recent photos of the telescope with a lot of progress on the actual hardware and construction. But also the comp cams, this is the commissioning camera, has been brought to the summit. And this basically begins the phase of commissioning, which here will be camera commissioning, and then soon it will become science commissioning. How soon? The expected date is the beginning of 2021. So in 2021, we expect to begin taking data, actually, sorry, with the SciComm at the last quarter of 2020 with the ComCam, and then at the beginning of 2021 with the full LSST camera. So this is how the commissioning phase will look like. Installation and initial testing, and then the key performance metrics that will be the tests that will be performed are the key performance metrics. So this is just to assess the image quality, etc. And then tests that make sure that the 20-year depth can be achieved, because that's paramount to the 4 science drivers, and tests of the scheduler, because that's paramount to everything. And then this is the really interesting part. This is when we begin playing with the data, where the science collaboration members should have access to the commissioning data, which will include mini surveys. The construction of the templates will happen in the first 3 weeks of commissioning. So templates for image subtraction and detection of transients. The mini surveys will be proposed as we submit the proposal, will be chosen from those proposals. And the commissioning phase will have 3 weeks for construction of template, 6 weeks for mini surveys, and the last 3 weeks is when we will be able to test the alerts release system and follow the alerts. I left in the slides a whole bunch of resources that go from our website, lsst.org, the news digest. Recently, we included all of the email of people in science collaboration to the news digest, which is something that gets in your email regularly so that you know about what's happening at LSST. Community.lsst.org, everybody has access to this board, but the science collaboration members have also access to protected areas of this board, and Slack, which you only have access to if you're in a science collaboration. There's additional resources, I'll just let you browse through them. And then one last thing that I want to highlight, there is a series of talks. The science collaboration chairs have a monthly meeting with the project, so the people that are building the pipeline and designing the survey, and where the project gives a talk on a subject that is being identified as of interest to the science collaborations. The people present at the talk are only the science collaboration chairs, and perhaps at some level of PI-ship in Europe as well. But the talks are actually released publicly on the website, so you can see the recording of the talk afterwards. They're particularly instructive. You can hear about the astrometry, photometry, pipelines were the most recent talks, but also, for example, the EPO system for education and the data release, etc. I think I'm done with this.
Thank you very much for this very interesting talk. I would like very much to go back to the slide in which you showed all the wide, fast survey together with all the other surveys that are currently planned.
Yes.
So I was wondering whether what is written in this slide is also written in the stone, in the sense that, in the sense of whether it has already been decided and fixed the fact that, for example, that we are not going to have the near infrared bands covering the galactic plane, what kind of cadence we are going to have there, or in highly resonant regions of the galactic bulge. So, because
excellent.
In reading the slide, it was, it's like, well, come on, let me, give me a break.
No, absolutely, absolutely. And that's really largely the reason why I'm so excited about this meeting, is because this is really the work that we need to do in the short term within TVS and within all the science collaborations. These are not written in stone. What's written in stone is that there will be a wide deep fast survey that will take a certain percentage of the time, which will depend on the details of the design such that they can fulfill the 4 science pillars. So once the wide deep fast does accomplish the things that it needs to accomplish for the grants that it received by DOE and NSF, which is the 4 science drivers, then all the rest of the time can be spent on mini survey and deep drilling fields. And so it cannot be written in stone because we don't know how much of that time is left still, right? So it will be radically different if the efficiency of the wide fast deep is such that we have 25% of the time as opposed to 15% of the time. And currently that time ranges between really 25 and 5%, so it can change quite dramatically. There will be a proposal call in the summer for mini surveys, and I just want to point out what a mini survey is sort of with respect to a deep drilling field. So think about a deep drilling field as a single pointing that will be done at a different cadence. And it's not like it has to get to a certain depth. Like it's not like all the deep drilling fields have to get to depth 28. That's not necessary. But it's a single pointing that gets done at a different cadence, at a faster cadence. I think it would be hard to push it being done at a slower cadence. But and then a mini survey is a collection of pointings that gets observed with a certain strategy for a specific science goal, or maybe 2 science goals if you wish. And so the proposals, there will be a proposal call in the fall with proposals due, in the summer with proposals due in the fall, specifically on deep drilling fields and mini surveys. So none of this is actually written in stone. In fact, you see 5 deep drilling fields here, and some of those, even without being actually written in stone, nobody is going to let go of like observing the ultra deep field or observing things that are in coincidence observation with WFIRST. But there are other pointings that may be of interest that are not included in these 5, and the number 5 is not mandatory. It can go up to as much as 10. That's what's being said. And again, it really can go up to as much as whatever we can convince them to do, given the amount of time that is eventually available. I hope that answers the question.
One more fast question. Just for me, the mini survey.
Yeah.
Do you really think that it will be start the beginning, 2022, as you say? Or
yeah. So the mini survey.
To test the telescope.
So the mini survey will be leveraged to test. I had it somewhere here, right? Will be leveraged to test commissioning. So they're referred to as mini survey in these slides that I did not make. They will be mini surveys in the sense that they will take proposals for compact surveys that can be done in commissioning with a specific science scope. And that some of them will require, also in the mini survey here, you had one of the, I'm not even about looking for that slide. The first mini survey that they mentioned in the first 3 weeks will be the construction of templates. That's a mini survey of sort. So I would interpret the term mini survey there as something that is ideally has a self-contained science goal and can be done in those 3 and then 6 and then 3 weeks.
This is something that we have to take into account when we write the proposal.
Yes.
Okay. So, thank you again, Federica. One question more.
Sorry. No problem. Sorry.
say that, of course, at some point, we hope that the scientific community will also provide a lot of inputs in order to have software included or something that has to be included in the general pipeline of LSST. Do you think that, I mean, anybody could, for example, provide his own software and then this will be developed at another order by technical people? Because, of course,
so it's a tricky question. And actually it's a question that I'm being recorded, but I'm going to say it anyways. It's a question that I wish the LSST project was spending more time answering. So the LSST project has committed to devote 10% of the computational resources to the scientific community, which will be able to access those computational resources and run on the data without having to download the data, essentially, right? So you will have, as a user, probably upon request, and maybe upon some competitive process, access to a remote machine that actually has direct access to the data, so you don't have to get the data home to process it. And then you can develop you can develop whatever software you want, whichever way you want to develop it. You can code without any comments for all you care. You can encrypt all your variables as A, B, C, and it's all code, you do what you want. If you think that that's an important product, and so if that's a product, for example, that is built by a large section of a science collaboration, I would recommend you that you think a lot about coding standards. And the coding standards of the LSST project are public. They're on the website. And thinking about, how they want you to code, PEP compliance, Python, coding rules, etc. Because then you give the chance to your software to be integrated in the main pipeline. Right. So a good example of that is LSST is writing crowded field photometry pipelines, but it's not a priority of the project. And so they encourage the science collaboration to work on their own crowded photometry pipelines and then to present it to the project, and it will possibly be integrated in the full data release pipeline. It has to work, but it also has to be consistent with their coding standards in that case.
Okay, thank you again, Felicia. And first of all, we talk about the relationship between INAF and SST.
Just a quick info about the wireless, the name.
Good to know. So what I have to use here? This one? Federica, is this black box here?
Mine.
Oh, shall I use this one, the black one, the blue one? Okay. Okay. So thank you very much for this opportunity. And I have to say that approaching the observatory, I was thinking that there are a number of premieres that we have to be happy with. I am familiar with this observatory now for more than 25 years, I would say, or something like that. But this is the first time that we have a new director, a woman director. It's the first time that we have a national meeting about LSST. And all these are really positive news. In particular, I will say that they are positive news because if we are here, probably when we started a couple of years ago to force the decision of the National Institute to support a number of PI ship participating to the LSST Corporation was a plausible, a good idea, because now is a reality, is no more a matter of discussion. During my talk, I am going to
mention some of the things that we already have, some of the things that we would like to have, and some of the things that are going to happen without or with or without our effort. And then there are a few slides for the conclusions. So let me start from where we are. And I think that for all those of you that have been involved with the LSST already know this list. This is the number of the 15 PI ships that have been approved with the name of the PI, the INAF institution where they come from, or they are associated, and the three coordinators for the working groups on stars, galaxies, and time domain astronomy. You can see that we are unevenly distributed because if we put together, I would say, stars and time domain astronomy that quite often have to do with stars, we are a significant fraction of the PI ship of the participation of the Italian participation to LSST. There is a long-standing problem, I would say, that strictly speaking have been approved the 16 PI ship, but the INAF is only paying for 15. And what is important is that the last year, Rolly Bedin decided to stop for 1 year, giving the opportunity to Ennio and Paolo Ventura to come in the LSST group supported by INAF. I know that this is one of the issues that we are thinking about, but this is my personal opinion. I would say that if we do not have, do you think that I needed this one? Okay. In case we are not going to have a sort of a natural solution of the problem in which every year there is someone that is spontaneously asking to stop for 1 year, we have to think about a criterion, a general criterion to decide how to do in case INAF is not able to find the funds for the 16th PI ship. But I have to say that, once again, personal opinion, that this might not be a real problem. And the reason is very simple. You have realized that a few minutes ago when Federica was showing the list of the membership of the different states to LSST, Italy is contributing with the 60 researchers. And this means that since we are a 15 PI ship, we should be nominally 75. The reason why we are not 75 is because, roughly speaking, only 50–60% of the PI ship are quintuplets. Several of them are not full. So in my opinion, when we are talking about other 3–4 colleagues that do need to participate to LSST, I don't see that this is a strong limitation right now. Obviously, we have pros and cons in all the possible decisions, but right now, from my point of view, this is not a strong limitation. Okay. Together with this, I know that probably this is a bit boring for those ones that are not involved with the LSST Italy, but these are the kind of information that allow us to participate in the meeting, to be a part of the LSST community, and there are a limited number of funds already available, and these are the funds that we are using to attend this meeting and also other meetings that are planning during the year. And we also decided to have a sort of a pool in which all the PI ships are giving a small amount of money that is going to be used for special opportunities or for organization of meetings that are not going to be supported directly by INAF. So this is a slide that I showed in November during the meeting in Monte Mario. And I was suggesting to have a meeting in January to discuss all together what could have been the opportunities for the mini surveys, for tidying up the Italian participation. And you know that this didn't happen. This is the first meeting, we are beginning of April. So this means that even if we have had good ideas, this was not the case. But you know, our community has always been very, very active in a number of different topics. And what happened, I am just giving you a very short presentation of some of the task forces that have been well, suggested or in which the Italian community is playing a leading role. And I have to say that one of the, this one that was about the variability in crowded fields, in which we are mainly interested in IZY bands for highly reddening regions of the galactic plane or the galactic bulge, is something that is something in which we would expect that LSST is going to play a fundamental role, because we know that Gaia, even if it is a perfect, wonderful experiment, is not going to be very, very efficient in regions in which the reddening is going to be very high, because the main band is the J band, even if there are also the B and R bands. Another task force in which I would say there is also a relevant participation by the Italian communities is about the supernova demography. And well, together with Maria Teresa and other collaborators, is important because this is going to play a role in what in the role that the cadence is going to have, the cadence of the images are going to have for the identifications of all kind of supernova, not only supernova type 1a that are very popular for cosmological reasons, but also for core collapse supernova and the kind of implications that we have. Laura, for sure, is one that is very much interested in this and is going to have also an active role in this kind of researches connected with supernova demography. Moving from the time domain to the, I would say, from the stellar to time domain, remaining in the time domain, this is another project for blazes by Claudia Raiteri, and this looks like as a, you know, a classical project in which you are looking for blazes, variability of blazes, but it is clear that LSST is going to open a new parameter space, because the intranight cadence and the multiband observations are going to play also a crucial role to understand the physics of these objects, for which there are decades of data that have been collected. And last but not least, the incredible connection that we are going to have in the near future between the legacy of Gaia, or what is going to be observed by Gaia, and what is going to do LSST in some of the in some science cases that are overlapping one with each other. Gisella, Tatiana, or Ilaria, I am pretty sure that they are going to talk about it. So this is just say a number of tidbits. Let me close with a slide that I received by Nicola Napolitano, mentioning or summarizing what is the involvement of one of the PI ship for the Galaxy working group. And you can see the number of people that are directly the A-type or indirectly connected with this project, and these are the working packages in which they are involved. So I would say that we have a clear evidence that the Italian community is doing well, is working in the right direction. Now, once we have clarified these issues, let me say a number of points that for which we do not have had already a clear view, a clear approach for what should be done. One is about the extra funding, because it is clear that with the funds that we have right now, the participation can only be limited to one researcher per PI ship. If we are talking about, for example, international meetings, we really need to have support, manpower, in particular, I would say PhD students. And there are another couple of points in particular, I would say, this is almost a joke, but probably you realize that the Lupin School is no more organized. This is the last one was the first year after 20-something years, for which INAF didn't support the Lupin School. And I have to say that this is a pity, because the educational part of the National Institute, in my opinion, is crucial. Is crucial because this is the role that all the other institutions abroad have. I am talking about the Max Planck, for example, Society, or the Leibniz Society, or the CNRS in France. All of them are strongly supporting and contributing for education. Unfortunately, INAF, for reasons that are not clear, is not supporting anymore. What is the connection with LSST? The connection with LSST is the fact that we need to have all the PI ship need to include a PhD student. And so if we are not going to have students, if we are not going to have students that have been trained to take advantage of what LSST is going to provide, this is something that we are going to miss. This is for sure. We can find individual solutions, we can find local solutions, but there is, right now, there is no national policy to identify what is the best strategy for the next generations. Keep in mind, just because in my department I am a minority and the bulk is from Geneva and from particle physics, now Geneva and the National Institute for Nuclear Physics are fishing among the master students, because they realize that this is quite important to have this direct connection with the young generations, and to try to, how to say, to support their attitude in science even before the PhD. So I would say that this is a problem, and I hope that sooner or later we will have new opportunities. The last one is about the meetings, because this is somehow connected with what I am going to tell you in a couple of slides. I think that I was suggesting to have more focused meetings for the LSST community, and this is becoming more and more relevant to the concerning the strategy for example, for the mini surveys, for what is the coverage of that LSST is going to have of the galactic plane of the highly redundant regions, and this is something that we have to start to discuss all together in such a way that we can find solutions that can be shared by a broad community. And this is exactly what I would like to spend a couple of words. And these on the same. This is the same slide showed by Federica. And I think that in the mini surveys, there is no doubt that the wide and deep surveys is the most relevant legacy for LSST. But we have the manpower and we have the possibility to play a role altogether, starting with the ComCam survey and ending up with the mini survey, to decide what kind of science we would like to do. We have the numbers, we have the capabilities for doing that. I'm not only mentioning those ones collaborating with Gaia, but all the community has already a number of expertise that can be naturally recycled. Someone was talking about crowded field photometry. This was a daily bread for a good fraction of the Italian community, the stellar community, for 30 years, 40 years. So I have no doubts that that we can somehow be involved in these kind of strategies that are important for the science that we would like to do. Now I would like to change a little bit the topic, and I would like to mention what happened a couple of months ago in Nice. It was organized by this meeting by Asterix. The first time that I received the email, I was convinced that it was a spam because Asterix is just a cartoon; it has nothing to do with real stuff. And it was not a joke; it was a reality. And there is a group. I realized what is the name of this acronym here: European Strategy Forum Research Institutions, in which there are already a number of, well, I would say, persons and meetings that have already been organized to discuss the synergies, even if this is a horrible word, between CTA, ELT, neutrino experiments, and SKA. The point is that all of them, you see, neutrinos, no bands, SKA, radio, ELT, near infrared, CTA, gamma. So what was missed there, and all of them, all of us during the meeting, I think that we called it hundreds of times, the crucial role that LSST is going to play in this business. Because it's going to be the only experiment that is going to cover in a single experiment 6 bands from the U band to the Y band. Okay? So this means that not only for ELT that is going to provide the targets for the spectroscopic follow-up, but also for all the other transients that are going to be detected in these different bands, it becomes crucial to think about on how to use the information coming from different wavelengths and different messengers. The reason why there was organized this meeting is because these guys are already thinking about the time allocation committees that have to provide time to experiments that are looking from the optical to the gamma. Okay? And you know that in some cases it looks like as a bit science fiction. You know, several of these experiments are going to become available on a time scale of 10, 15 years. But the point, the real point, is that they are going to happen, and those ones that are going to have access to time domain in the optical are going to have, for sure, an advantage compared with all the others. Okay? So why I am saying this? I am saying this that because Italy is involved in all of these projects, but there was no Italian there, no official Italian invited to this meeting. And this is once again, in my opinion, a limitation, because even if it was a sort of, like a bottle left in the ocean, these are the things that are going to become more and more relevant in the near future. And I am happy now to say that at least for the, let's say, the ISO community, this is going to have some support, because CTA is north and south, but the south is inside ISO, where there is ELT. So there are a number of opportunities, I would say, in any case for the Italian community, because it's ISO that is going to do that for us. But we are not officially present in this kind of business. And in my opinion, this is a limitation. Okay. Now, these are talks, words, but this is a slide that, for I would say, where is Abby? But Abby, this is something that I received from Deepak, and credits are for ISA Deepak CU7. In a single shot, you have something like 551,000 variables that have been detected by Gaia. And what is interesting here is that this is what Gaia has done with the depth that is 20.7 in G band. Gisela, correct me if I am wrong. 21. Okay. So can you believe what how is going to look like the same plot once we are going to have a depth that is 5, 6, 7, 7.5 magnitudes deeper than this. You can see, well, you don't need to be an expert. These are the Magellanic Clouds, the galactic bulge, the external regions of the galactic bulge, the region of the galactic plane that are with a limited number of stars because of due to the reddening.
According to Astrostatistics, you have to multiply by 4 for each magnitude.
Okay, so this means 2 million. Okay, well, very happy. But I am already excited with the 500,000. You know, I think that astronomers like Sandage discovered hundreds of these objects. Am I right, Abby? Probably thousands. We have had the microlensing experiments that were moving on tens, thousands of them, 20,000, and in a single shot, Gaia is increasing by at least, I would say, almost 2 orders of magnitudes as soon as we are going to have the complete catalog. So why this is important? This is important because we are lucky. Our generation is a very lucky generation because we are going to have simultaneously in our scientific life the results from Gaia, and we are going to have LSST, we are going to have JWST, ELT, but for sure this is not something that we have to wait for. They are going to become available in 2 weeks, and I don't know of any other event in the history of astronomy in which we have this specific date, in which the day after you wake up and you can find on your computer 500,000 variable stars. I know you can live without them, there is no doubt. But for those ones that have spent a significant fraction of their life in looking for the physics and the astrophysics of these objects, this is for sure something that is quite exciting. Okay, let me move to the conclusions. And they are very simple in the sense that I have to say that honestly, the Italian community did really a good job in the last year or so, and activity, the scientific activity, well, I think that this was somehow already mentioned by Federica. It is something that is moving in the right direction. Obviously, we are a very diversity is the common feature of our community, but even if we are we have to live with this diversity, I think that we are following similar paths, and this is quite important because this means that there is a lot of room for improvements, in particular for what I have mentioned before concerning the scientific collaborations inside the LSST participation. We have still a number of pending issues, but it is clear that is because we have many different opportunities, and all the times that we have to deal with so many different opportunities, there are pending issues that need to be fixed and solved. And I will say that I will stop here, and that's it.
Question?
I'm not sure exactly what the question is, but just to say that the science collaborations haven't really had a lot of European PIs, and the European PI-ship and membership, has its own rules. So I think we need to spend a significant amount of time thinking seriously about how we have a regular science collaboration structure interacts with your structure and allows you to, pursue and achieve these goals. I think it's an interesting question. It's very important to look at. And then I encourage the people that you mentioned that are experts in product photometry. One of the talks that I mentioned are available on the LSST.org website. is about the plans for product photometry of the LSST project and their encouragement to write pipelines for that. That would be a fantastic opportunity for the Italian. For the Italian.
Yeah. We have a man, we use a sentence, we have a uomo alla Havana. The man, the Havana's man is Massimo D'Allora. He's going to be sacrificed for the crowded field photometry. He's very happy about that, and we are happy with him. But obviously, all the others, Tatiana, I think that is also, and others. I am sorry if I am remembering only a few of these names. Are very happy for collaborating on this. I thank you very much for this, for stressing this point. These are the kind of situations in which we are not coming from nowhere because we have our own history. And the Italian participation, one of the reasons for supporting the Italian participations was, to LSST was exactly this one. The fact that we already come with our own background, and we would like to take the advantage for this kind of background that we have. And I think that LSST is the right gym for doing that.
LSST wants to take advantage of that background as well.
Thank you very much.
You mentioned that substantial fraction of the fly ships, Italian fly ships, are not quintuplet but less quintuplet. And I think that this is because of the definition of the quintuplet, how it has to be made up. And it has to be made up with young people, young students, and it's not easy to have the students in the quintuplet. So how do we solve this conundrum? It's a problem.
Laura, thank you. This was a lively. We have had a lively discussion during the last meeting in November, because there are rules that have been fixed by LSST, and there are rules that are general definitions for what is a postdoc. Okay? If we apply I would say the Anglo-Saxon definition is a young researcher, but others consider a postdoc every researcher that has not a permanent position. And if you look, for example, to the German PI ships, there are young researchers that have 40, 45 years because they do not have a permanent position. Okay, so I fully agree with you. I fully agree with you. So the point is that we do not want to force any rule, but it is clear that in this, I would say, at least in this warm-up phase, I will not be too strict in what are the postdocs, because we cannot change at all the students, the PhD student, because this is a clear definition all over the world. But what is a postdoc? And we have had a number of discussions with the LSST board corporation to have more details about that, and at the end they suggested to tell us is not a faculty, it might be a faculty member, it might not be a faculty member. Is someone that is at the early phase of the research life, but it might not be at the research life. So there are degrees of freedom, and I will not complain if someone is including a differently young researcher, let's say in this way. This is my opinion.
Okay, thank you, Giuseppe. Thank you.
Anyway.
Luis, the data release plan.
You want the remote?
Okay, hello. Thank you very much for inviting me today. I'm very excited to be here and to talk to you about the LSST data products, the data release plans, and how you can start to work with the LSST data. So just as a quick introduction, I have only just started in this position. I'm the new data management scientist for LSST. I'm taking over from Mario Juric, who has been doing this job for quite a number of years. I have not actually officially started yet, so I'm sort of pre-LSST at the moment here talking to you, so I'm still also learning on the job. I expect to start in mid-May 2018, and I will be based at the LSST headquarters site in Tucson. Some of you may know me from Gaia and CERN, and I'm very happy to see so many of my old Gaia colleagues here today. So just a quick look at LSST, where it is. The site is shaping up, and you can see that it's very close to completion. The dome, which is conspicuously not there, is planned to be finished in mid-2018. There is networking partially in place, internal cabling is being done, and it's very exciting to see the site looking like it's going to look in the end, looking quite a lot like that. And if you're interested in following the progress, there's a website. You can follow what's happening at Cerro Pachon if you want to keep up to date. So Federica has also already showed the schedule. I won't go into too much detail about it, but just to say that data management here is about halfway through its program, and we're just coming into commissioning right here. And the focus now for data management is going to be commissioning. How do we start to commission our pipelines? How do we build an integrated system? How do we start to do the science validation with all the data management pipelines and for the data products that we're going to produce? And so commissioning, you can see, is going to ramp up here. ComCam will be on the summit later this year. And yeah, it's looking busy. So LSST data management. The LSST camera and telescope collect data at about 20 terabytes of data, raw data per night. And the data management system takes this data and it processes it automatically to produce data products. And the data products are images, catalogs, and alert streams, essentially. And so the alert streams come in what we call prompt data products, which are produced nightly and put into alert streams. We expect something like about 10 million per night, with a latency of about 60 seconds. And 60 seconds is from the close of the shutter after the second exposure of a visit. Expect to have that alert. This produces a prompt database, and it's a living database and is updated nightly. We also have data release data products which are created annually. And these are produced by running science pipelines which process all the data that has been collected to date. So this is based on the nightly data, and this is based on all the data collected to date for a data release. It often involves running more complex algorithms that require more computing resources, and so you get a much, much richer data set from this. Over the full 10 years of the LSST lifetime, there will be 11 data releases, resulting in a 15 petabyte database catalog at the end. And so finally, how do you get to use this? Well, this is where we come to the LSST science platform. Data access is via data access centers that we're building and the services that go with them, which together comprise what we call the LSST science platform. So the LSST data products. Federica has already shown you this as well, but I'm going to go into a little more detail about what happens inside of these. So they're organized into three main categories, and you can find the detailed descriptions in the LSST data product categories document. The prompt data products are a stream of about 10 million time domain events per night, detected and transmitted to an event distribution network within 60 seconds of observation. There will also be a catalog of orbits for about 6 million bodies in the solar system. And as Federica pointed out, quite importantly, these used to be called level 1 products. We don't call them that anymore. We call them prompt data products. So how do we create these prompt data products? They're created through difference image analysis. DIA, and you'll see this acronym quite a lot, DIA, difference image analysis. You take the visits, you take difference images, and you take catalogs of objects that have already been detected and run a whole series of pipelines on them to do image subtraction, to look to see if you can detect a difference image source at a 5 sigma level, And if one is detected, then a series of measurements and processing is done on those sources, including forced photometry, which on the data in the existing data in the catalogs. These pipelines produce output objects. These are objects in the database, a different image analysis object, source, and forced sources. And so, from within 60 seconds of the shutter close, an alert will be generated and issued to the stream, each one for every new difference image analysis source that is found in a nightly processing. And also the prompt data catalogs. These are the catalogs that contain all products from the prompt data processing in the US Data Access Center will be updated. Within 24 hours, the force photometry of the past 30 days of images for objects will be computed, and raw and processed images will be made available in the US Data Access Center. And so this is what you can expect. Just note that prompt processing also includes the nightly identification of solar system objects, but I won't go into that in detail today. So what exactly are these prompt data products and the prompt database? It's a living database that is updated in real time every night. And it contains objects and sources that are detected on difference images. Just a little bit more detail, this is a non-exhaustive list of what you will contain in a DIA source. You'll have information like the signal-to-noise ratio of the detection, the coordinates, associations with existing solar system objects or existing objects in the catalogue, time of mid-exposure, shape parameters, etc. In the DIA objects, you'll have coordinates, fluxes by filter, information about periodic and non-periodic variability features, and also there will be a link to nearby objects in the data release catalog. And just remember, the data release catalog is created once per year, and it's a very rich data set which has been produced with all the data to date. So having this information available together with the new sources in the prompt catalog can help you with your science. So what goes into an alert? In the alert streams we've talked about, these data products that have been produced in the prompt processing, the difference image analysis, are packaged up into an alert package, which will contain at least, again, this is not an exhaustive list, and there's still discussion about what might go into it, but it will at least contain an alert ID, a database ID, and the science data, including the difference image analysis source that recorded the trigger, the entire difference image analysis object that is associated with it, the previous 12 months of source records, and matching object IDs from the latest data release. And there will also be cut-out images of the source. At this point, I might just point out for some of my Gaia colleagues in the room that source doesn't mean the same thing in LSST as it does in Gaia. In Gaia, what we call a source is what LSST calls an object. And a source is in fact a single epoch observation, which we call just an observation in Gaia. So that might be a bit confusing for Gaia people. Oops. Oh, sorry, what was that? Sorry, what happened? Yes, but okay. Sorry, I don't know what happened there. Okay, so that was the alert packet content. So how do we distribute these alert packets? They get distributed. Oops, sorry, I keep clicking the wrong button. They get distributed. I'll put that down. They get distributed via a queuing system. They get put into an alerts database, and then a queuing system is used to push them out to community brokers and to a small LSST broker that we call the mini broker. So there are two types of brokers here. Community brokers, which are the primary endpoints for the LSST alert stream. We expect these to be provided by third parties. There will be a finite number of them chosen by a proposal process. And these brokers will receive the full stream of LSST data alerts, which can be filtered and then distributed out to users within their community. The alerts will be transmitted in what I'm going to call a community accepted format and using IVOA protocols. Possibly this will be a VO event, but the VO event might evolve. But whatever the format is, it will be something that is known and accepted by the community. So users can then take these events, they can filter them, classify them, and use them to follow up on science. And of course, trigger follow-up observations as well with other telescopes. The LSST mini broker is a much smaller version of this, which is accessible through the LSST Science platform. It contains user-defined filters that act just on alert packets. So this means that there's no facility to do cross-matching with this, that you can only work with the mini broker on what is in the packet. Access to these filtered streams is via the Science platform at the US Data Acquisition Center. And as this is a much smaller version of what we expect the full community broker to be, there is a cap of about 20 alerts per user per visit, and there is a limit on computing capacity for this sort of thing. So it would be more of an exploration use case. Okay, so what's the next class of data products? Is data release. So they're the prompt data products, and that's what you'll get nightly in the alert streams, that you can look for transient events and trigger follow-up investigations. The data release products are produced annually. This is a catalogue of about 37 billion objects, 7 trillion observations, that is sources, and 30 trillion also measurements, these are forced sources, that are available through online databases and via the LSST Science platform. Also included will be single epoch and deep added co-added images. And for anyone who worked in the Gaia variability processing group, what happens here at the data release level is pretty much covers these work packages that we used in Gaia, the calculation of statistical parameters, time series characterization, and some very basic variability classification based just on simple statistical parameters. So there would be no in-depth modeling, but just simple statistical analysis. So what's in the data release products? You have here you have well-calibrated, consistently processed catalogs and images. You have catalogs of objects, detections in difference images. Often extensive computation is required here that combines information from many exposures. And this very rich data set is made available via what we're calling a data release, which is performed yearly. However, in the first year, there will be a data release after the first 6 months. So there'll be 2 data releases. Data release 1 will be after 6 months, and then subsequently they will all be annually, which will give us 11 data releases over the 10 years of the LSST timeframe. And one important thing to note is that in this data release, the living prompt database, which contained the objects, the data products from the prompt processing, will also be fully reprocessed in this yearly reprocessing of the data set. And so the prompt database will also be updated. Access to these catalogs is via relational databases in the LSST Science platform, and there will be remote access APIs provided using VO protocols, for example, the table access protocol. Projected sizes, something like 18 billion objects in the first data release through to about 37 billion in the last. We go from a few petabytes in size to about 70 petabytes in data release 11. So it's very large volumes of data we're talking about. So what's in the data release catalog content? There are images, single visit images with the instrument signature removed, background, PSF, 0 point, etc. determined. Difference images, deep coads across the entire survey. In addition to images, there will be sources and forced source catalogs, which give the location and times of detections, information on deblending, model fits, seeing independent color, and forced photometry on all exposures. This is again a non-exhaustive list. Objects, there will be characterization of objects on multi-epoch data, photometric redshifts, periodic and non-periodic features of the objects, proper motions and parallaxes. So I'm going to take this just now to talk a little bit about, in terms of variability characterization, what you might expect to see. The data release production has post-processing pipelines, and one of these is a classification pipeline which computes variability summary statistics and probabilistic or discrete classification of each object. And it does this on light curves from difference image analysis objects or objects. The light curve variability is characterized by 2 tables, the aperiodic and periodic. And these are all derived from the light curves for each band separately. There is a list of all these parameters given in detail in the Science Pipelines design document. And I'll just cover a couple of parameters here because I understand that there is a task on the Transient and Variable Star Science Collaboration to review these parameters and to give feedback on what's in the database at the moment. So just as a quick overview, there is in the difference image analysis object table and also in the object table, you have an LC periodic and an LC non-periodic field, which contains periodic features extracted from light curves using a long scalable periodogram and the non-periodic features are mostly just statistical parameters. So 20 parameters for the aperiodic, things like standard deviation, slope, trend, skewness, a lot of these statistical attributes you will recognize. And for the periodic, there are 32 parameters calculated for each band. The long scalable periodogram is used to find 3 fundamental frequencies with 4 harmonics, and coefficients, linear coefficients, amplitudes, phases, phase differences, etc. are all provided as well. And I think from the science collaboration, we're looking for some feedback on this. So does that suit your needs and how you would use it? So I've just given you a bit of a look at some of the data products, a quick introduction to what some of them look like, the information that you will get, how you might use it. But the list of data products is exhaustive, is extensive. And we have here, excuse me, an LSST database schema browser that you can go to online, have a look, pull up these information about the objects and have a look and see what information is stored, what will be transmitted, what can you work with. And so here, for example, I have the, this is the difference image analysis source that we were just talking about. You see it as a source ID, it's associated with an object ID, a solar system object ID, etc. And there are many, many more parameters there. So if you want to really delve deep into what's in the data products, go and have a look at the LSST schema browser. Just a quick few points on data release availability and retention. Once produced and validated, a data release is frozen and it's archived. We don't go back and update a data release after it's been validated, frozen, and released to the community. So this facilitates future access, but it also facilitates publishing based on specific LSST data releases. You can tie your publications to a release. It's not feasible to keep all these data releases, given the volume of data involved, loaded and accessible at all times. So the current policy is that older releases will be on mass storage, and the current and the penultimate data release will be available through the science platform for people to work with. If you want to get access to older releases, you can have bulk download them. But most of the time, users will work with the most recent data release, and they will perhaps go back to the one beforehand to check out if they've redone an analysis on the latest data and they see some differences and they want to go back and compare with the previous one. But there aren't that many cases where people will go back to much older ones. So that's something to think about as well in terms of your science analysis. All the raw data used to generate any public data release will be made available for download as well. Okay, so now to come to the last category of products that we work with, these are the user-generated products. These are produced by users yourselves, they're not produced by LSST. These are value-added products, near-Earth object catalogs, variable star classifications, shear maps. These are all correspond to your science goals and what you want to do with the LSST data products. They are enabled by services and computing resources at the data access centers and through the science platform. So resources will be made available to run these user-generated pipelines. And so again, for my Gaia colleagues, this basically corresponds to the detailed variability classification and everything that fell under the specific object studies in CU7 variability analysis. So all your Lyria and Cephei code for the Bologna team, you would write this in a user-generated environment. And you would write your software, possibly use some of the LSST software and run it in this user-generated context. So they're created by the community, as I said, using LSST software services to enable science cases that we do not cover in the prompt and the data release processing. For example, custom processing of deep drilling fields or custom algorithms or detailed classifications of variable stars. A few points. LSST will not write unique algorithms for reprocessing the main survey data, but we will make available the LSST software stack source code, which the community can then use and extend or reconfigure to generate new user-generated products. And I think it was already mentioned, 10% of the computing resources will be dedicated towards enabling this end-user analysis and generation of user-generated data products. And again, I think this came up in a discussion just before. User-generated software and products may be migrated into the data release production level with the owner's permission at the discretion of LSST if we feel that there's added value to run this in the data release pipelines, if we want to include this in standard releases, So this is really it's not going to be a blanket statement that you can include it, but if you would like to, then this is open to discussion and we can see if it can be done. I think, as was mentioned before, observing coding standards and documentation standards will greatly help in this if you are interested in migrating your code into the data release production level. How much longer do I have? 5. I will skip that. Okay, I'm not going to go into detail on the special programs. You all know what they are. They're basically anything that's not the wide, fast, deep survey. And the idea is to improve the science, to cover different areas and to address different science use cases. There was a call for white papers back in 2011, which led to the definition of the first 4 extragalactic deep fields. What I want to say here simply is, and it's been said already, is that there will be another call for white paper proposals very shortly this year in June, and we are looking forward to receiving your proposals. The call will go out very soon, but the basic driver for this is that science evolves and science changes over time, and 2011 was quite a long time ago. So now, before we get first light in 2020, now is a good time to undertake a final commissioning pre-optimization of the LSST observing strategy. So we're looking for input from the science communities as to how to optimize the LSST cadence and observing strategy. Just a couple of points about data management and the special programs. There is a document that was produced which details how special programs, data products and pipelines, how we will deal with them, how we will treat them, and how the data will be released. But a couple of points is that we will not write unique algorithms for processing special programs data. We expect that we should be able to use the algorithms that exist, perhaps slightly reconfigured with a few different parameters, but we won't be writing special pipelines. 10% of the computational resources will be allocated to processing the special programs data. If it's scientifically beneficial, like for the user-generated pipelines and data products, we will incorporate these into the alert and data release productions when scientifically beneficial. And again, the software stack will be made available to the entire community. So just finally, I'd like to talk now about the LSST Science Platform for enabling science. And what is it? It's a web-based service available to the science community, which allows you to access the data in the LSST databases, catalogs, visualize, subset, and perform what we call next to the data analysis of LSST. And this means that you don't have to download masses of data. You connect to the science platform and you run your analysis next to the data. It's a set of integrated web applications and services deployed in an LSST data access center. This includes both software tools and computational resources. There are 3 different aspects to the science platform. There's the user-facing aspect, which is a portal, which you can use to explore the data. There's a Jupyter Lab environment, which you can use to write Jupyter notebooks and explore the data with your Python code. And then there are web APIs, which allow you to integrate with external tools that you might be using already. This enables access to both data releases and the prompt database and alert streams through the data access centers. I'll just quickly give you a look at what each of these aspects look like. The web portal aspect is a window onto the LSST archive, which allows you to browse, visualize the data sets that are available. There are many existing archives already. So you can just run exploratory analysis of your data. You can do simple selections, view LSST images, request data sets using forms or SQL, construct simple plots. It's basically an exploratory tool which allows you to take a quick look at the data. If you want to get into a bit more depth, though, you can go to the Jupyter Lab environment, which allows you to run Jupyter Lab notebooks. It is identical, in fact, to working with the Jupyter Lab notebook. And you can run this Python code next to the data. So the computation and analysis resources are provided by the LSST data access centers. And this enables science discovery by letting you run your software on the data at the data access center. Environments are set up that have pre-installed libraries with common tools like AstroPy, LSST Science Pipelines, and you can also install your own favorite tools as well. So you can set up your environment, there will be a standard environment, and you can also configure your environment to do analyses. The LSST Science Platform with its different aspects is an integrated environment, which means that data queries are shareable across each of the different aspects, across the portal and across the Jupyter Lab aspect. So if you submit a complex SQL query in a notebook, you can then go and browse the results in the portal. So you have this fully integrated environment. And finally, the web-based API aspect, which allows you to integrate with existing tools, like here we have TopCat and DS9. The LSST data is exposed via these BO interfaces that enables you to link in with external tools. I believe you can do this with the Gaia archive as well to link in TopCat. So if anyone has played with the Gaia archive with TopCat, it would be very similar to that. So, and again, because it's an integrated environment, when you build a query using the Portal Query Builder, you can access the results remotely via Jupyter Lab or via TopCat. So you can bring all of this together. And these are the three aspects on the Science Portal which allow you to explore the data, get a feeling for it, visualize it, and then start to run what could be quite complex analysis. Okay, so just finally, I'll wrap up by saying, how do you get involved? How do you communicate? How do you feedback? It's already been mentioned that we have the community forum, which shows you the community forum here. There are many discussions here. If you need help, if you're trying to do something you don't know what to do, go to community, ask a question. Every science collaboration has an interface to the data management team, and so at least, at minimum, your interface to the Transient and Variable Star Science collaboration will handle your requests and queries, or perhaps delegate them to other people. And I just provide here a list of references and contacts. These are some documents that describe the processing system to you. There's a data products definition document, science pipelines design document, and the science platform document. And these give you details of everything I presented today, plus a lot more if you want to go deeper. Ask questions at LSST community. I have a request that any questions about data pipelines and products should go to the data Q&A channel on community. So that's where you want to go there. This is moderated by the subsystem science team, and approved answers will be generated and posted in a timely fashion. Your points of contact for Transient and Variable Stars in data management are Melissa Graham and Eric Bell, and you can always contact me as well if you want, subsystem scientist. Thank you.
Thank you very much. It's time for your question.
So, can you hear me?
Mm-hmm.
So I would like to you can tell the data, the pipeline is ready, and what kind of the data are you using to test it, and how much of interaction is with the community, because I mean there are many simulated LSST images runs, people with desk collaboration, for instance, they're preparing a data challenge with the LSST images. So I wanted to know how much, I mean, the work on the data pipeline is uniform with what the collaboration are doing on
Do you mean the science pipelines?
Yeah, yes, the science, yeah.
Sorry, so the science pipelines that we run to produce the prompt products, the prompt databases, and then, yeah. So at the moment they're being developed internally, they're being tested, and they're being tested on HSC data. We've also used desk data as well internally to work with this, and there are people internally who have contacts in those collaborations and they work with them. As we go into commissioning and as we start to go into science validation, I expect that we will start to involve the science communities a little bit more at the science use case level to validate the products and the pipelines and so forth.
So much interaction is currently going on, because for instance there are some issues like background subtraction. This has, I mean, this depends a lot on the kind of data you're using.
Yes.
So how much of this activities
You mean interaction with the collaborations?
I mean, if there is a data set, a reference data set where you can build.
Okay, right. Do you mean is there a reference data set made available to the science collaborations already at the moment that you can work with? Is that what you mean? Probably not. I don't think there is at the moment. I will follow up on that, but right now I think that we're still doing internal verification of these things, and that's not ready yet. But we do intend to involve the science collaborations in this work.
Okay, thank you again, speaker.
source classification for transients. The community has been invited to provide information specific interested. So to the alert task force. So the question is regarding your slide showing the community alert and the mini
broker,
where this information will be implemented, or whether the information will be used in a in a subsequent case.
Can you give me a little bit more detail about what the information is that you're providing?
We have been receiving a TPS alert broker task force to provide information regarding source classification. Okay. So the community has been invited to provide colors, timescale variability, and so on. So the question was whether this task force alert will work in one or the other slots that you have shown.
Of the different data categories? Do you mean in the different data categories?
Maybe I can clarify this a little bit. So you're talking about the survey that was initiated by TVS, right?
Yes.
Right. So the TVS has a task force, among the task force that has been done recently, to look at what data products we will want from a broker. So I don't think
right.
this is
Okay.
LSST.
Yeah.
This really has to do with what we will ask the brokers like comparing.
Exactly.
The broker that is being billed to give us that. Although there is the mini broker.
So in the mini broker, you won't be able to access the full data set, and there will be filters. So perhaps some of this information will be able to be encoded in user-defined filters in the mini broker, for example. But it won't be very complex, so you won't be running classification AI algorithms to do this. It will be very simple things. In the community brokers, however, you need to talk to your community broker provider, community, because it really depends what they're going to implement. LSST makes the data available, and then the brokers will pick this up and provide it to the community. And how they decide to filter that, how they decide to distribute that, how they decide to make that available to users then is up to actually the community brokers. I think that's probably where your question goes.
Can I still ask? What is the time window in which we can influence things like the variability parameters that will be released with the prompt data? You mentioned a few that will
yes.
be released, but there could be more.
There could be more.
7 closest galaxies or whatever.
Sure.
How long do we have?
How long do you have? I can't give you a data at a time. I might go back and ask about that. I'd say as soon as possible if you know them. I mean, don't wait. Okay, it'll be easier to implement them earlier on and easier to put them in. So, but I'll come back to you to see if there's a cut-off date for that. But I think that this is going to evolve over time, and even as you start to process the data, you're going to learn more and might want to update things and change things. So, I don't.
As soon as possible is tricky because nobody acts upon it.
Exactly. No, I know. Nobody does. Yeah, but I would encourage you to take a look now if there's a task force that is already reviewing those periodic parameters for that would be very good to get feedback on that.
Either 1 minute.
I was wondering if the source ID of a source is going to be the same through the releases, or is going to change. So if I'm working with some
I know what you mean. It changed in Gaia. Have you worked with the Gaia data? It changed with every Gaia data release. I don't know. I'll come back to you on that. I'll find out. It's not going to be the same. Okay. But yeah.
Thank you.
Thanks again, the speaker.
Just a quick communication. We are going to have pixel light on the seaside. So for the people interested in pixel, please sign up on the
short presentations, just 5 minutes talks, and this is the schedule. All the speakers, yeah, no, okay. Where? Here? Yes, here. Okay. So all the speakers will talk together without any break. So questions, you can make questions after this short presentations, okay? Now we start with Silvia Piranomonta. She will talk on the astrophysical sources of gravitational waves.
Okay, yes. Okay, hello everybody. Thanks to Maria Teresa and Amata for organizing this very useful workshop. So let me present. I'm Silvia Pietromonte, and I'm taking part of the group of LSST Italy group, which is dedicated to the search of the astrophysical source, which are the electromagnetic counterpart of gravitational waves. And also in this group, we have people who work with variable X and gamma ray, the variable X and gamma ray sky. So let me present you the group. The PIs are Enzo Brocato, Marco Tavani, and Marco Feroci. And here we are. The junior researcher are Giovanni Piano, Giulia Stratta, and me. And our scientific and technical interests, of course, are the gravitational wave sources, gamma ray, X-ray transient and binaries, blazars, and tidal disruption events. So the participants are very, very much more. So these are all the people who are interested in these topics and who wants also to work with LSST data when we have them, we'll have them. And so our first goal, of course, in our group is the identification and the study of the electromagnetic counterpart of gravitational wave signals. And as you can see, LSST will match very, very well the multi-messenger area, which started just some months ago in August 2017. And here you can see the timeline where we will work together with all these gravitational wave detector, together with some of the future observing facilities we will have in the next 10 years. So, as everybody knows, you know that we can certainly say that the multi-messenger era has begun because thanks to the gravitational wave event 170817, which was associated with a neutron star merger, and from this merger we were able to see also the light from this event, where the Italian group, together with international collaboration, made a great effort in order to discover the kind of the transient, which was a particular transient called the kilonova. So the Italian group was one of the first group who could identify, thanks to a very almost daily spectral sequence of spectroscopic sequence, we could identify this very particular transient, which is called kilonova. So just to show you the whole data set we had for this event, not only from Italy instrumentation, from Italy facilities, but also Italian facilities, but also from all the other instruments which observed during this very big observational campaign. So here you can see all the spectra associated with the kilonova emission, and here you can see all the light curve in different filters which were taken during several days, also after some weeks. You can see this transient which was very near. So here you can see how this kind of transient decay very fast. So in this sense, we have to study also the particular cadence we need also in order to work with LSST data. So what about the other kind of sources we are interested on are and these are the blazars, of course, and also the tidal disruption events. And for each of these objects, we can have different cadence and different light curve because of the different behavior of these kind of sources. So yes, okay. So what about LSST? We want to work with LSST. So we work together. We work inside the subgroup which is dedicated to this. So gravitational wave sources and multi-wavelet characterization of these sources. The leading group is Raffaella Margutti, who will talk about LSST tomorrow. And so this is our, this just to show you what we need in order to work with LSST. Okay, so we need to have information about the transient alerts, and this information will be the position, the timing, the magnitude, and also some preliminary classification. And also we need to do also follow-up later during the day. So we need to have image and photometric multiband data in order to deconstruct also light curve and different filters. So the objective for us will be to have to exploit the direct availability of the full LSST data to select specific electromagnetic counterpart candidates, because after the selection we can follow with spectroscopic facilities these particular sources in order to have the real characterization of this transient. The second objective is that is the one to have finally, for the first time, simultaneous optical data together with the data which come from Agile and Fermi, because the problem is that often Agile and Fermi have to provide a wealth of data which are not simultaneous with optical data, and so in this way, LSST will allow us to overcome these issues. So these are all the sources which we are interested in working on: collecting transient and binaries, optical flare and long-term monitoring of laser, gamma ray bars, gravitational wave source counterparts, which of course where gamma ray bars are inside also these sources, and exotic transient like the tidal disruption events. So things to do for us now is to explore the discovery and the discerning power of LSST with the matrix analysis framework, using template of non-transient, especially the faded ones. Interface with brokers, I finished. So give them a list of critical things that we need from them, and then you have to work and design the best target of opportunity strategy for electromagnetic counterpart of gravitational wave, and I think that Raffaella Margutti will talk about it tomorrow in detail. So this is our present and future activity. So we are working on matrix analysis framework. We are working in photo simulator, and we are working also in coordination with other transient Italian group like the Gamma Ray Bars group, which is the one with will talk now. So thank you very much.
So next speaker is Salata, okay. You will talk on gamma ray bars and tidal disruption events. So you can put down on that. Okay.
Okay. Hello, everybody. So I am part of the group at the Brera Observatory in Milan, and our PI is now Sergio Campana, and we focus on gamma ray bursts and tidal disruption events. So just a brief recap of these sources. So in the left part of the slide, we have gamma ray bursts. This is a sketch of the standard scenario of gamma ray bursts. You have a stellar mass compact object, which is undergoing accretion, and it launches a relativistic jet, which, as it becomes transparent, it releases the prompt radiation, the gamma rays, so the actual gamma ray burst. And then, as it interacts with the ISM, it begins to decelerate and gives rise to an additional component which can be detected in all bands from high energy down to radio, which is called the afterglow, and which is mainly due to synchrotron radiation. And these are example light curves of how such an event looks like. In the X-rays, you can see the prompt emission and then a decaying part, which corresponds to the afterglow. In the optical, usually you don't see the prompt, but you can see several minutes or hours after the prompt a peak, which corresponds to the onset of the deceleration, and then the decaying part. Actually, in most cases, the jet is not pointing towards the Earth, so what you actually expect is that you are missing, because of relativistic beaming effects, all the first part, and you are only seeing rising and then decaying afterglow, where the peak corresponds to when the relativistic beaming cones intercept the line of sight. And in this case, you would call this event an orphan afterglow. There is actually no convincing detection of such an event to date at any frequency. Maybe GRB 1708-17A is the first example of an off-axis jet, but we are still, the debate is still ongoing. But we would really like to have the discovery of this kind of source with LSST. The prospects are good. Tidal disruption events are to some extent similar situations. You have a compact object, in this case it's a supermassive black hole, and you have accretion of material which comes from a tidally disrupted star. You can see the radiation from the disk, from the accretion material, and in some cases you can also have evidence of the presence of a jet, and this is the case we are interested in because we have expertise in modeling of the jet properties. And so we are a rather small group. So the core team is the people in red. So it is Sergio Campana, Giancarlo Ghirlanda, Paolo D'Avanzo, and two postdocs, which is myself and Andrea Melandri. We also had a PhD student, Deborah Mainetti, who left, so we are looking for a replacement. But we have many people supporting our work, collaborating with us, which are the people in black. And we are working basically on two main topics, which is rates, predictions, and modeling of the population of gamma ray burst and TDE, and strategies, so classification strategies and follow-up strategies, which is more or less in overlap with Silvia's work. So I will only talk about this topic, which is the main topic I work on actually. So we already made predictions for the rates and the properties of orphan afterglows from long gamma ray bursts, and we have already revised previous rate estimates for long GRB afterglows to be detected by LSST, and now we are extending our approach, which we dub CK, population synthesis code plus hydrodynamics and emission, to short gamma ray bursts and also to kilonovae. And so we are validating the modeling, and we are near to be able to generate our population and extract the predictions about rates and properties expected to be detected by LSST. And the next step is to find out how to actually make more LSST specific predictions by, let's say, putting into communication our CK approach with the stack, so with the op-sim and maybe also the fall-sim, to find out what are actually the expected rates and properties of these transients and how can we recognize and distinguish them from other transients. And so that's actually the next step and the ongoing work we are doing.
So, Andrea Sorello will talk on the peculiar transients with LSST.
Okay. So, yeah, my main interest is basically studying peculiar transient with the LSST. To go, sorry. Okay. Basically, I'm interested in the transient that lies in these areas of the luminosity versus decline time scale diagram. So intermediate luminosity optical transients, which are transient with the absolute magnitude intermediate between those of classical novae and Kerr-collapse supernovae. Then the upper part, the superluminous supernovae, which magnitude exceed those of thermonuclear supernovae, and then the right part of the diagram that is populated by fast transients. Then I'm also interested in studying failed supernovae, so the so-called dark supernovae. So basically, objects that undergo core collapse without producing a real supernova explosion. And this is a pretty nice candidate from Adams et al. So basically, I'm interested in disappearing stars. Superluminous supernovae are objects whose absolute magnitude exceeds minus 20.5. They can be either hydrogen-rich or hydrogen-poor, like these are objects shown in this diagram, and they are all formed in faint dwarf, very likely metal-poor galaxies. Which is the explosion mechanism is still under debate. They can be either nickel-powered pair production supernova or pulsational pair stability events, or more canonical core collapse supernova powered by the magnetar spin down, or ejecta CSM interacting supernova, a combination of these mechanisms. Another part of the project is on supernova impostors that are basically giant stellar eruptions that can be either single outbursts or even multiple outbursts of a very much longer eruptive phase. Typically, they are associated to luminous blue variable stars. In some cases, this kind of transits produced also a real supernova explosion a few years after. This is the case of O9AP, which produces, after 3 years of uninterrupted activity, a real core collapse supernova explosion of type 2. We have observed something similar also in hydrogen-poor stars. This was very likely an event produced, an outburst produced by Wolfram Yesari in 2004 that was followed 2 years after by the real core collapse supernova explosion as a peculiar type 1BN supernova. Then our goal is also working on some other types of intermediate luminosity optical transients. Faint stripped envelope supernova that can be different types of transients that can be either peculiar thermonuclear explosion, but also in some cases some types of underluminous core collapse supernova. A class we are very interested in is the intermediate luminosity red transient that are spectroscopically faint type 2 supernovae. They have peak magnitudes ranging from -12 to -14, and they are associated with progenitors that are 8 to 10 solar mass stars embedded in dust environments. So they are good candidates to be electron capture supernova from super-Gibbs stars. And finally, we are interested in working on red novae. We can have either galactic faint transient like V1309 Scorpion, but also much brighter counterparts observed in the external galaxies. They had quite peculiar spectroscopic evolution and a bizarre double-peaked light curve. And well, the interpretation of this transit is can range from some type of stellar eruption from single moderate massive stars, or even some type of binary interaction, producing a common envelope phase and eventually a final merger. So this is basically what we require from LSST. Okay, here there are the different type of science we want to perform with LSST that require quite different follow-up strategies and eventually the support of different type of facilities. Just a few words on the preparatory phase. One of the main goals of our activity is basically producing quite good templates of this type of rare objects. For this, we are working with several telescopes. Unfortunately, not many INAF facilities. And the idea is to provide to the community a database of, my idea is around 100 objects that will be released after the publication of the studies through a web interface, in which we want to provide light curves, we want to provide spectral sequences, all the details of the calibration, the physical classification, and so on. So all kind of information that should be publicly released. Thank you.
Okay, thank you. Is Massimo Brescia. He's talking on the supernova demography and rates based on machine learning.
Thank you. Okay, our project is included within the three science collaborations, the Transients and Variable Stars, dark energy in terms of photometric redshift estimation and galaxies. And this is the four people belonging to the official quintuplet. According to what explained by Giuseppe, myself is one of the typical example of very young scientists. Also, of course, there are other participants. In particular, Maria Teresa Botticella is the PI that was replacing Laura Greggio since the beginning of this year. Sorry. Well, the main focus of our project is essentially to provide a classification of different subtypes of supernova in order to essentially associate these different supernova types to their progenitors and to study the relationship between them. So we want to answer to specific few fundamental questions. For example, just a few, which are the progenitors of each subtype of core collapse supernova, if they come from different channels, young and old stellar population, which is the mass range of CC supernova progenitors, and how depends on the metallicity, the different evolutionary scenarios leading to supernova. And of course, to answer to this question, we want to, of course, provide a large, for statistical reason, unbiased sample, and of course also a deep understanding about the galaxy properties in order to characterize the stellar population according to the star formation history and metallicity. Concerning the procedure, we want to perform such scientific goals by first starting from a valid simulations of different supernova types, and to obtain a catalog of light years sufficient to apply our machine learning classification mechanism, automatic system that must be required in terms of efficiency dealing with LSST huge samples of data. And in order to perform the classification of these supernova types, we want to characterize, tune, and validate some methods that come from our past experience, direct past experience. For example, in this work, we extracted from the Catalina real-time survey a set of data of light years that we map into a statistical parameter space in order to have the possibility to train some machine learning methods able to classify all the subtypes of the supernova. And it is also mentioned by Liana's presentation just before about this set of periodic and aperiodic statistical parameters useful to characterize the light curves. For example, for the Catalina sky survey, we obtained some results concerning different types of classification experiments, going from the disentangling between cataclysmic variables and versus all, or extragalactic versus galactic, or supernova versus all the other types, in which the performances reached are very promising. Okay, so we try to reuse this experience. In order to perform such exercise, we are trying to gather at other catalogs. And for example, from the DES simulation, we intend to reuse this public catalog that is provided. And there is also a Master of Science thesis running on this work right now. Essentially, we try to disentangle different subtypes of supernova, and by starting from the simple exercise that is the classification between two classes, for example, the supernova versus fake objects, or to disentangle supernova of first type with the second type. It is quite simple in terms of classification experiment, trying also to approach more complex examples in which we try to disentangle 3 or 4 classes. And as you can see, there are some cases in which the lack of purity and completeness demonstrate essentially what we have learned, that we need a huge amount of data in order to validate these examples. And that's it. Thank you.
Next speaker is Maribel Caldereros. She will talk on blazars with LSST.
I am Maria Isabel Candela Martinez from the Observatorio Astrofísico de Torino with the PIs Claudia Maria Irratairi and the John Research is Barbara Malvaverde, Filippo D'Amando, and Chiara Rizzi. Barbara Malvaverde is here with me. We studied the blazar with the LSST. The blazar is a type of the gene. The gene is the most violent variable. The gene they normally have 2 jets. The peculiarity of the blazar is that one of the 2 jets is pointed toward us, so that the relativistic effects cause amplification of the jet emission and contraction of the variability time scales. The blazar emission stems from the radio to the gamma ray frequency and show variability at the all wavelengths. The temporal variability at the several scale is model-real, but sometimes there is an outburst. The spectral energy distribution of the blazer, there are 2 bumps. The first is for the synchrotron, and the second is for the quantum inverse. But we can see in the near infrared and the optical part, we can see at the other small bump. We can do a zoom this region, and we in the first case is the type of the blazer with a ratio 0.04. This one is for the contribution, for the strong contribution of the host galaxy, and this other blazar have a is dominant for the jet. The ratio is 0.9, and this other blazar have a ratio more or less 2.1, and is dominated for the accretion disk. For study the blazar, we need to build the light curve. Here is a example. This is the long-term light curve for more or less 5 years in the different optical bands and the near infrared. In the flare epoch, the source have a six magnitude of variation. In this part, we can study the intraday variability, and this show in a few hours 0.5, 0.6 variation, more or less. For we are doing a different test for the LSST. In the first case, for the main survey cadence, we build different lake curves with the different data sets. For example, the web, the Stewart, Kite, Catalina, Smart. We extracted the light curve with the main survey cadence. I take one point B. After 3 days, I take point in B. After 3 days, I take point F. At this point, I create the synthetic light curve in F with the average of color index. In this part, I plot in black the real light curve and in red the synthetic light curve. This says that the main survey is good for the study of the variability, but not for the intraday variability because I haven't sampled something. For this, I need the drilling fields. Other study is for the identifying new source. We study the colors and the variability. For this, I take the paper of the Butter and Blue. They study the state 2 of the plot and plot the color. This the study is for the quasar and the variable stars. This green point is the quasar and the red is the variable star. But this not is good for identifying new source because there are this region is very complicated. The same we are doing for the blazes, but it's the same. No, it's good for identifying new source. For this, we study the variability. It's the same. I take the Butter and Blue test. They take 4 parameters, 4 different parameters to identify the source. In this case, with these parameters, the quasar are here and the variability is star are here. I use this type for the blazer, for the different type of blazer, different regimes. All blazers are here. And the other parameters is this. All quasar are here, the variable star are here, and we use the blazer. All blazer are in this part. The square is the all light curve, and the cross is the synthetic light curve for the main survey. In this moment, only I use for the 50 blazer. I need this is preliminary result, but I need doing with more. And then finally, we build a database for blazer for the LSST. I haven't time for explain, but if any person is interested, I can show. Thank you.
Thank you. The next speaker is Alberto Moretti. He will talk on AGN and galaxies with LSST.
Okay, wish to thank you, the organizer, for inviting me and for giving me the opportunity to give a short report on our project, which is actually very far from the time domain astrophysics. Indeed, it's focused on the early universe, and the title of the project is The title of the project is AGN and Galaxies. AGN and Galaxies in the early universe during the ionization epoch with LST. We are 4 PI, myself, Alessandro Caccianiga from the Brera Observatory, Andrea Graziani and Angela Bongiorno from the Rome Observatory. And for this year we have 3 postdoc, Claudia Ciccone DOAB, Emiliano Merlin and Valerio Roscani from the Rome Observatory. We also have a PhD student from the Insubria University, funded by INAF in the 33rd cycle, Silvia Belladitta. And the goal of our project is the measure of the relative contribution of AGN and galaxies to the ionization of the intracluster medium, the study of the early evolution of the supermassive black hole formation and the coevolution, their coevolution with the early galaxies. In these fields, well, to these purposes, statistical sample of very high redshift quasar are essential. So in this, with this respect, LSST will be very useful and probably will significantly transform this field. So this is the current situation. Let's see how. This is the current situation of the high redshift quasar observation. Basically, we know 15 quasar between redshift 6.5 and 7.5, which has been selected using the UKITS LASA survey, Viking survey, and PanStar survey, which we consider a useful precursor of LSST survey. And they are identified in this part of the color plot. Here on x-axis we have y, j color plotted against the z and y color. Basically, all these 15 objects have been identified in this part of the in this corner of the plot, where they are well separated from the low redshift interloopers, which are basically brown dwarf and elliptical galaxies at redshift around 1. They are basically all type 1 quasars. And these are the numbers of LSST. We expect that after 1 year, after the second release, actually, the 1 year release of the photometric catalog of LSST, we will detect 1,000 quasar around 6 and something like 100 quasar around 7. This is the plot of the expectation as function of y magnitude. This is the limit of one single observation. This is the limit of after 5 or 10 years, I don't remember, survey. So this number represents an improvement of more than 1 order of magnitude with respect to the current situation. But the key point is that all these objects will be relatively easily identified in the LSST catalog. Indeed, thanks to the very deep survey, we expect that the contamination of the photometric catalog will be 20–30% to be compared with the actual usual contamination, which is above 90%. So our activities in Brera for this year, we spent 8 nights at telescope in the last 2 months, just to get a deep photometry of different samples of high redshift candidates. Basically, this is the game we play. We start with an object with a spectrum, with a photometric SED, which is very in the infrared, which is very close to high redshift QSO, but with the optical limits given by the Sloan or the PanStar, we cannot distinguish quasar from local elliptical galaxies. So this is with a very deep optical point in E or in Z, we can distinguish the two templates. You see that here we don't expect any emission from the quasar, while the elliptical galaxy is still emitting. So we selected 2 samples in this way and observed at TNG and NTT. The first sample consists of a candidate to be quasar beyond redshift 6.5. The second sample is given a radio loud sample between 5.5 and 6.5. We are also working on a blazar sample And blazars are very important in our view to measure the census of accreting black holes at high redshift, because, well, since they are we are seeing on face on their jet. If we detect one blazar, actually we expect that there are at least 100 or 200 objects like this in the universe. So finally, we are also working on a new detection technique which combines data from the space and from the ground, and this will be very useful combining Euclid and LSST data. Sorry for.
Thank you.
So next speaker is Tatiana Muraveva, and she will talk on Gaia LSST synergy.
Hello everyone, I am Tatiana Muraveva, and I am member of the quintuplet, which works on the synergy between two great projects, which is Gaia and LSST, with particular attention to pulsating stars, star formation history, and white dwarf planets. So basically, PI of this quintuplet is Gisela Clementini, who works in Bologna. She has particular expertise in variable star distance scales and stellar population tracers. Then there are two co-PIs, which is Vincenzo Ripepi, who works here. And he also had a huge experience in studying of variable stars, distance scale, and stellar population tracers. And then there is Roberto Silvotti, who works on white dwarf planetary systems. Then there are junior members, which is Michele Cignoni, who works in Pisa, and he's our expert in star formation history. And then there is Felicio Cusano and myself. We both work in Bologna. Then we have a junior member, a PhD student, Alessia Garofalo. And there are also other participants. Oh, sorry. Other participants all over Italy. So I believe that our scientific interest regarding LSST is well described well seen in the activities that we performed during the first year. So basically our group works on, let's say, three connected directions. So majority of people are working on synergy of Gaia and LSST regarding variable stars, in particular large stars and Cepheids. These are me, Gisella, Felice, Alessia, and Vincenzo. Then Michele Cignoni, who works on star formation history, and now he is making tests with the HST and in future James Webb Space Telescope. And then we also have a part who is under supervision of Roberto Silvotti, who is working on the planetary transients with the white dwarfs. So very shortly about what everyone is doing. So Gisella and Vincenzo have worked a lot on the Gaia pipeline dedicated to classification and characterization of variable stars. And you will see the products of this work on the 25th of April, so it's arriving. And this is, we believe that their experience in the pipeline for Gaia will be very useful for the LSST data and for the development of the LSST pipeline. Then next, it's from my part. We believe that it's important also to create catalogs of variable stars, like Cepheids and large stars that now available in the literature will become available with the Gaia data release. So these catalogs will allow us in the future, when the LSST data will become available, to test the performance of the LSST and in general to make science. So I'm working on the creating this catalog. This is, for example, for field RLR stars. In the same time, there is a person who works on the collection, and it's a bit more complicated, a collection of RLR stars in the clusters and in dwarf spheroidal galaxies. So we already have the catalog of these objects, And we believe that it will be very important in the future also for the LSST. Another member of our team, Felicio Cusano, since we want to use RLR stars, I will go very fast now. We want to use RLR stars to study the structure, different structures in our galaxy. And in close galaxies, Felicio Cusano has developed a code, Python code, which will help him to study the structures with these pulsating variables. Then we have Michele Cignoni, who is working on the code developed to study star formation history of in galaxies within 20 megaparsecs. This code has a name Sphera, and it will also be, now he is testing it on the HST data, but he will be used later, applied it later to the LSST dwarf galaxies. Then there is part of the, as I said, white dwarf planetary systems. So now we are creating catalogs of white dwarfs, for which we are interested to find the planetary systems, and Roberto Silvotti is working on this. So altogether, everyone has its own part to work in preparation for the LSST data. And we are also involved in some task forces, this one actually, and these are the names. So the majority of people, basically, we all working on the DDF and me, survey proposals playing. So far, we are on the level of documentation, so we prepared documentation in collaboration also with the quintuplet of Marcella Marconi. This is some ideas from this documentation. I am more involved in another task force, which is stellar variability in crowded fields. Basically, we want to choose to select some data set in the crowded field, like in the bulge of our galaxy, and try to test, first of all, to run, for example, DAO on this field and to understand if we are able to recover variable stars. And then to use the same data set to test the LSST pipeline. But Massimo, I think tomorrow will talk more about this. So basically, this is again what we selected so far. We are planning to study these fields and to check variables in these stars, and then to apply the LSST pipeline to the same fields. And finally, the last one is the variability characterization parameters task force. We also prepared documents, so it's on the level documentation, but the work is in progress. And thank you.
So now next speaker is Ida Moretti. She will talk on RLR effects and luminous blue variables with LSST.
Thank you, Mata. So, RLR stars, effects, and luminous blue variables to constrain theory using LSST data. The PI of the project is Ilaria Musella, and the co-PIs are Marcella Marconi and Marco Limongi. Then there are several young researchers, among which me, that is Maria Ida Moretti, and other co-workers all around Italy. We are affiliated with two science collaborations, and they are Transients and Variable Stars and Stars Milky Way Local Volume. So, something about RLR stars and Cepheids. What we expect from LSST data? We expect that this data will better constrain to an unprecedented level of accuracy the relations that stands at the basis of their uses as primary distance indicators. So we expect to constrain also better the distance scale and the Hubble constant. Then, of course, we expect also to derive the 3D structure of the objects that we are going to study, and to constrain the physical and numerical assumptions of the model for RLR stars and Cepheids and luminous blue variables. Okay, I will say it later then. What is important is that, as already done in the past, we are going to compare the theoretical light curves with the actual observed data from LSST data. And to do this, we are going to compare the theoretical light curves with what we will be observed, specifically for the filters from LSST data. And this is something that was already done in the past by our group, for example, with the Sloan digital sky survey filters. For what concerns the luminous blue variables, what is the main point? The main point is that we expect to better model these stars that are quite difficult to model because of the chaotic ejection of the mass. And so, in particular, we are also interested for what concerns the gravitational waves. We expect to better constrain the duration of the LBV phase and the location in the HR diagram of the stars, and also to better constrain the total amount of mass ejected, both in total and per eruption. And here is an example of the position of these stars in the HR diagram through different level of metallicity from 0 down to -3. And for what concerns future scientific activity and synergies, what we can say? We can say that we expect to plan to have a set of multi-filter light curves, and so also to investigate the LSST time series data, and also to study the classification of the sources that we are going to study, and also to use the follow-up, spectroscopic follow-up. To do this, we are already involved in some ongoing surveys, and also we are involved in a project for future telescopes. So in particular, several of us are, several people of the team are involved in Gaia, and this is very important if we think that LSST is the fainter counterpart for Gaia, as was already said before. And several of us, some of which also me, are involved in VMC. VMC is a survey that is studying the Magellanic Clouds in the near infrared, and so we have more than 12 epochs in the KS band, both in the LMC and SMC and in the bridge. So we have a counterpart for LSST. And for future telescopes, we are involved in projects for James Webb Space Telescope, and also for ELT, which will be let's say the possibility to have the spectroscopic follow-up. And thank you very much for your attention.
Thank you very much, Ida. And now next speaker is Ennio Boretti. He will talk on multi-periodic phenomena in variable stars.
First of all, I am very happy to be in the row of so many young researchers. It's quite surprising. And then I will. My team was the 16 team past year, and so we were on the bench. And now we are an official team, but I am still on the bench because the PI now changed. This is Paolo Ventura. We unfortunately cannot be here, and Marcella Di Crescenzo as well cannot be here today. Will be here tomorrow. So I give the talk for them. And there are also other collaborators in Brera Observatory and Roma University. Our tool to investigate the instability strip, exactly this part, which is the point. Our tool is to investigate the instability strip, that it is located here in the Hertzsprung-Russell diagram, and there are many, many variables. And our tool to do that is quite simple, is the Petersen diagram. LSST will produce very dense and very long time series. You analyze this time series in frequency, you extract the frequencies, and for the classical pulsator, you can easily identify the main pulsation mode, which usually are radial modes. And then you can construct the Petersen diagram simply by putting the long period on one axis and the ratio between the short and long period on the other one. You can see that the stars are not distributed by completely random in this diagram, but are following some sequences. And these sequences are characterized by the different pulsation mode. That would be the second or the third overtone as in this case, or the first and the second overtone in this case, the fundamental and the first overtone, and so on. And you can easily construct this diagram for the Cepheid, and then you have double or triple mode, and also for the Magellanic clouds, and then also to do that for our galaxy. So we have a quite simple tool to investigate the stellar structure and to separate pulsation mode. The scientific goal for this is for the Cepheid. For the error layer is the same, in the sense that you can obtain the same Petersen diagram, and then you can identify easily different pulsation mode and different sequences. There are some strange feature here because we are discovering many and many stars which are a quite unusual period ratio, this one, and it is not fully understood exactly how it is. And again, we can clearly separate a different pulsation mode, and you can investigate what is the difference between the star following this, for example, this curvature. Another item we recently added is the search for RLI stars in binary. It is a hot topic because at the moment we haven't any genuine candidate of RLI star in a binary system, and this is not clear why. It can be something connected with the evolutionary status of the star. Maybe they are binaries and the RLI star was englobing the other one, coalescence. There are many exotic theories, but in any case, there are some candidates of RLI star in binary, and then we are progressively trying to screen them to verify if some of these stars exist. On the top of the statistic, they are the asymptotic giant branch variables, and there are some long period variables. And again, these stars are not very much studied from ground, and so there is a lot of interesting physical research can be done. For example, it has been found that these variables are characterized by some infrared excess connected with the presence of the secondary modulation. It's quite simple. We have just star with 1, 2, or 3 modes radially excited, and you can, just studying this mode, you can do a detailed investigation of the stellar structure. And maybe the long-term variability is the presence of a dusty disk. It is a quite old hypothesis, but our PI, Paolo Ventura, investigated how this possibility plays in the dust formation process around the star, and then to compare with the evolutionary model. This is a very, very useful tool to do that and to investigate this possibility. So what we expect to learn from our investigation is to obtain information about the stellar structure, because the period ratio depending on that, investigate an unusual period ratio, and again to search for infrared variability and secondary modulation as tools, because we now know that the infrared variability amplitude is not the same as in visual. And again, we are trying to find RLI variables in binary systems. This is our best candidate. You can see clearly the variation of the omega that it is periodic and can be the lifetime effect. At the moment, for this study, it is the most promising target. We obtained last year the first radial velocity curve, and we have observation in a couple of months to confirm or not, to disprove the binary nature. Last is just the facilities. We have just added at the end the Tarot telescope, which are robotic telescope able to monitor RLS type periodically, so we can do a much more dense also analysis of the OMC, because they're provided from this telescope. And we are planning also to do some technical developments, searching for period shorter than the LSST cadence to investigate the short period variables which are located in the lower part of the stability state. Thank you.
Thank you. Next speaker is Simone Antoniucci. He will talk on star formation and episodic accretion with LSST.
Thank you. Good afternoon, everyone. I'm Simone Antoniucci from the Observatory of Rome. This is our group working on the young sources. It is formed by people from the Observatory of Palermo and the Observatory of Rome. The group of Palermo is led by Francesco Damiani, who is the PI in charge this year, and is formed by Rosaria Bonito, Sara Bonito, Loredana Crescenzano, and Laura Venuti also. And they work mainly on characterization of acrylic sources in young clusters. Then there is the Rome part, composed by Teresa Giannini, who is the co-PI, and myself, who instead work on young eruptive variables, which are basically young transient. So today I will talk mainly about these TVS sources. Okay, why LSST is useful for studying young sources? Because it can provide information on accretion, basically. Here you can, here you can see a plot of the standard scenario for accretion in young sources. In the standard scenario, a low mass star is basically formed on timescales of about 10 to the 7 years, with an initial accretion rate of the order 10 to the minus 5, 10 to the minus 4, 10 to the minus 5 solar masses per year. That slowly declines to values of the order to 10 to the minus 9, 10 to the minus 10 solar masses per year in later stages of accretion, in which the star is visible in the optical and appears as a classical Titori star, and later on as a weak Titori star. In this standard scenario, what we observe is that the sources are show lower accretion luminosity than expected. So the hint is that this discrepancy can be explained in terms of a highly time variable accretion. That is, the accretion is not stable or continuous, but proceeds through bursts. Here you can see this phase, the Titori phase, in which you can see this strong brightening, several magnitudes in the visible, that corresponds to the so-called FU or Ionis outburst or EXR outburst. And in between these strong outbursts, you can see the standard accretion. Let's say that a small accretion, a small variation in the accretion is a defining feature of the Titori star, and this is what is studied, for example, by people in Palermo, in young cluster. While in Rome we focus on these brightening events. These are associated to enhancement of the accretion by orders of 2 or 3 orders of magnitude. Here you can see the typical light curves of these objects, strong FU or outburst, in which we register an decrease in magnitude of 5 or even 7 magnitudes, and shorter and weaker brightening in the EXR sources. And it is not clear if this stage of evolution is common to all young sources. And it is not even clear what is the mechanism, the onset mechanism for these accretion outbursts. Why? Because we know so far only about 30 of these objects. And this explains why we don't have a statistical base to infer if these objects are common, this phase is common to all young sources. It is clear that LSST will hugely improve these numbers. Okay, we have, this is a summary of the typical photometric features of the outburst. You can see these FUR outbursts, which are much stronger than EXR outbursts, but EXR outbursts are recurrent. So we have these typical bursts that last months and are recurrent on timescales of about 10 years, for example. LSST will help us to discover tens, hundreds of these objects, and to improve the statistics, and also understanding if there is a periodicity which can give us information about the onset mechanism. Why LSST is useful for accretion? Because Basically, accretion causes an increase of the UV excess. So the U band especially is very sensitive to the accretion. Here you can see the Balmer jump, which is enhanced during burst phases. And it is using tools like the color core diagram U minus G, G minus R. It's evident that we can highlight the sources which are actively accreting. Okay, just a few take-home messages. LSST will help us to increase the number of candidates accreting objects and to study also standard accretion in young clusters because it is sensitive, especially in the U band, to accretion. Of course, candidates can be located studying the light curve, the SED, and this color core diagram. And the statistic will help us understand if the burst phases common to all young sources. The required temporal cadence is not that critical in this case because the time scale of these events is weeks, months, so this is the cadence we require to identify and study the light curves on these objects. Thanks a lot.
Thank you. So next speaker is Michele Trabucchi. He will talk on 3 legal and LSST simulations.
Hello everybody. So I'm Michele Trabucchi from the University of Padova, and I will talk to you about the simulations we are doing, synthetic population simulations for LSST with PI Leo Girardi. Some quick information about the people working with us. So the group, of course, Leo Girardi, and then we have 2 PhD students, Giada Pastorelli and Piero Del Tio. She's working directly on the computation of the simulations with the Trilegal population synthesis tool, while Piero Del Tio is currently involved in the implementation of some prescription for binary evolution in this tool. Yang Chen is a postdoc that is also working on directly on the computation of the simulations, while I'm working on variability in the implementation of variability information in these products. We are working in collaboration with the Starkey project, PI Paolo Marigo, in which many of us are also directly involved, and with the Parsec team, Stellar Evolution team in CISA Trieste, and the Milky Way working group at the University of Washington, and the LSST groups in Brazil and Chile. And our goal is to produce complete simulations to be probed by LSST observation. What does it mean? That we want to simulate the stellar content that we will find in LSST observations. And this means synthetic stellar catalogs complete with position, proper motion, photometry, of course variability information for the observations, and stellar parameters, so distance, extinction, etc., mass, effective temperature, and so on. We are working on in a 3-stage plan. So the first step that is completed is concerns single stars, detached binaries, populations, catalogs for the Milky Way, and the Magellanic Clouds. Step 2 is the implementation of variability information. That's what we are interested in today in this meeting. And since I'm currently working on what was my PhD project on long period variables during the HB phase, what we already implemented is periods, sort of amplitudes, and we are working on light curve for this kind of stars. I will explain why sort of amplitudes. And we are beginning to work on CFIDs and RRI. The third step is already it's work in progress, and will concern interact barriers, microenhancing events, and transits. So, okay, just to finish on the simulation part, this is a stellar density map of the newest simulations that have been carried out with the collaboration and resources of the University of Washington. And here is a snapshot of the region of the Magellanic Clouds, including Milky Way, foreground. These are the numbers of the simulation. But just to go on the variability part, this is what I've been working on recently. This is an observed period luminosity diagram obtained for long period variables in the SMC, obtained with OVL3 data together with JHK photometry from the 2MASS catalog, and compared with a simulation of the SMC to which we added variability information. This is done by interpolating each target, each simulated star in a grid of models. And the advantage of this approach is that it allows us to have a global perspective of these observations. One of the important results we had in this is that we found out that very likely these two sequences, you can see 5 sequences here, these 2 sequences are actually due to the same pulsation mode, which is the first overtone here. And this is something that was not possible to understand using only single pulsation models, possibly applied to isochrones or evolutionary tracks. And this is due to the fact that with this approach, we can account for the detail balance, some way subtle, between the excitation of modes that populate this diagram with respect to the depopulation effect of simply stellar evolution and star formation history. And this also helps us to both calibrate the theory, especially in terms of something that's very uncertain, like convection. And as for the amplitudes, an advantage we found of this approach is that the growth rates, theoretical growth rates, are behaving very likely to the amplitudes. So even with without nonlinear models, we can do predictions on the amplitudes. And this is also
Thank
it.
you. Next speaker is Germano Sacco. He will talk on photometric metallicities with LSST.
Hello everybody, I am Germano Sacco from the INAF Astrophysical Observatory of Arcetri. I will present some results obtained within the group led by Laura Magrini that include also some people from Padua. So our group is part of the Milky Way collaboration, and in general our group study the formation and evolution of the Milky Way and of its stellar population using astrometric, photometric and spectroscopic data. So in the context in the context of LST, at the moment our goal is to derive a relation between photometric properties of between photometry and abundances, so metallicity and alpha element abundancy. In particular, what we want to do is refine the method to derive from photometry metallicity and calibrate this method using the Gaia ISO survey. The Gaia ISO survey is a public high resolution spectroscopic survey carried out with the Flames optical spectrograph at VST, which is observing about 10 to 5 galactic stars in different, which cover a very wide area of the HR diagram. So, what we are doing now and where we start is to start to use the Sloan digital sky survey to and recalibrate the relation obtained for the Sloan digital sky survey that's been already derived by Iverich et al. In the 2008. This plot is a plot that describes log G expansion of G Menar for all the stars in common with between Gaia ISO and Sloan. These are only 3,000 stars, of course, because the two surveys are in different hemispheres. So we started with the temperature versus color relation, selecting a sample in the same color box defined to derive the temperatures versus color rotation in the slow and in the past, and you see we find a nice correlation, and the RMS that we found it's 200 Kelvin. So this is for what happened for the metallicity. This is the color plot again of the star in common with Gaia ISO in a specific color box, and with the color scale I indicate the metallicity measured by the Gaia ISO survey, and fitting fitting the relation between a combination of two different colors with a polynomial function, we can derive the photometric metallicity with an RMS of about 0.25 dex. In the plot on the right, I show the distribution of the residuals between the spectroscopic metallicities and the metallicities derived from this relation that we calculated with this fit, and the distribution it's not completely symmetric because there are some problem for the very metal 2 star, which are clearly very peculiar around this area of the plot. So okay, this clearly is a work that is starting now, a work in progress. Now we want to move from the metallicity to actually the derivation of the alpha element abundances from photometry. The different relation will be validated using data for stellar clusters that are very powerful calibrators. And then we will also try to extend our work to different color interval that have been not covered by previous studies, and cross match also Gaia ISO with SkyMapper, which include it's on the south, so which include a very large, much larger data set. Thank you.
Thank you. The next speaker is Nicola Napolitano. He will talk on stellar and dark matter in galaxies and scaling and mass scaling relations from the local universe to redshift 1.5.
Hi everyone. This is a kind of a off-topic talk because we heard about Transients so far. This is a project which aims at exploiting actually the static capability of LSST. In fact, LSST will provide is a big area with a great image quality and depth. We want to study properties of galaxies, possibly up to redshift 1.5, and characterize the stellar and dark matter content of these systems, and possibly also measure the distances. So this is a project that I'm coordinating together with Michele Cantiello, and there is also a large number of people that is going to help. The one on the tops here, you can barely probably read, are the ones that are directly involved, but then there is a lot of people that we are actually using their experience in order to make the tasks that you want to perform for LSST. And we are actually benefiting by our long track experience in large surveys, ground-based large surveys, like the ones of the VST, for instance, and particular KIDS, which is the deepest and highest quality survey, which is, it's meant to measure weak lensing, but it turned out to be very interesting for galaxy evolution studies. So here you see a breakdown of the different working packages that you want to perform in this project. We will perform galaxy classification. We will look for gravitational lensing. but we want to also test machine learning tools in order to handle this big, large data that we heard LSST will provide. This is an example of what we want to do based on morphology and study of structure parameters and the scaling relation of galaxy. These are some images from a kids survey again. The idea is that we want to measure the two-dimensional light distribution and characterize the properties, the structure parameters of galaxies. What LSST will provide is a large area, as I said, and an incredibly much larger depth, so up to 3 magnitude deeper. That means that what we are not actually doing in galaxy to study galaxy at redshift 0.5, we will do for to go much further than redshift 1. And possibly we will also take advantage of WFIRST in the near infrared to have a very panchromatic view of how the size, magnitude, Cersei index of this galaxy evolves across time. Of course, I mean, we are well aware that this big data time, so these classical tools here, but we are also starting experimenting machine learning tools to speed up things and do things on these large data sets. We're talking in LSST of a number of galaxies of the order of billions, which is, in some sense, is really astonishing. Also, to start with, we are actually working on simulations. Here are some example of what I said, the simulation from desk collaboration. So we doing this work, we collaborating both with the Galaxy Science collaboration and with desk for our interest on dark matter too. Here an example of the first data challenge. You see some of the simulation we're working on. Some parameters, but we are waiting for DS2, which is DC2, which is a much more improved evolution of these simulations, and we can start testing our tools on these images. This is an example of the first test we've done. You see here the galaxy and the results. I mean the residual images. The second part of the project is the study of the SBF. The SBF is a surface brightness fluctuation in galaxy. This is more local universe. So we're gonna use the surface brightness fluctuation to measure distance of galaxies, and with the depth of LSST it would be possible to cover a volume, an unprecedented volume, up to 200 megaparsec. This is a project that some of our collaborators in Italy are starting to talk and discuss with US team. And of course, I mean, here you see the maximum distance reachable with the different epochs. So the more LSST epochs will be, the more we go further in distances. So as I said, I mean, here there is a breakdown of the schedule of the project. Of course, I mean, most of the work in these years is on preparatory surveys and ground-based data already available, and there is a lot of developing of tools, but then waiting for the data for LSST here. Just a short summary of the activities. We are again collaborating with these two science collaboration, Dark Energy and Galaxy Science. We have been participating to the GSC, the Galaxy Science Collaboration Roadmap. We are lately hired as a new postdoc working on strong lensing. We have also PhD students working within this ITN network, this European network, which is meant to develop machine learning tools for next generation service. And so our idea is to test the tools that will be developed within this European network we are part of, to work first on the kids data, which are the current data we have, and then to develop tools that will be useful for LSST. Yeah, that's a minor activity about SBF, because this is more like a project that is really needing LSST data to come. And I'll stop here. Thanks.
Okay, thank you. now next speaker should be Andrea Biviano, but Andrea cannot be here, and also nobody from his project can be here, so I will shortly present his project. His project on the cluster of galaxies as probes of cosmology and also dark matter and evolution of cosmic structures, in particular for galaxies up to redshift 1.5. This project is the main aim of this project are the cosmological models, the test of cosmological models, and the investigation of the internal structure of clusters. So the cosmological models will be tested with the number density, the investigation of number density, and the spatial distribution of galaxies from photometric data. And also the internal structure of cluster will be investigated through the analysis of the the internal distribution of stellar matter and also diffuse plasma. To build a catalog of cluster of galaxies will be used the cluster finder Amico, which is developed by Bella Gamba, which is one of the people involved in this project. And as you can see from the plots from the left to the right, there's the contours of the errors of the uncertainties on the cosmological parameters. In green are the old contours, but with LSST we can reach this precision. That is a zooming of this part of this plot. Then, from the comparison between strong lensing and X-ray contours, we can also have information on the distribution of mass, stellar diffuse plasma. And finally, for galaxies, this plot shows the number density of galaxies with different properties, red and blue galaxies in clusters. So this project will be in synergy with also other surveys like Euclid or KIDS, XMM cluster outfit project. And a lot of people are involved in this project, in particular for this year. Andrea Biviano is DPI and Mario Radovic the co-PI, but also during this year there are people with the TD contract, Marulli, and also postdoc like Mauro Sereno. Other people were involved in last year, but Andrea recommended me to say something like what already people before said, that the problem of this project is to have no money for supporting young people that are now that are working with other kind of contacts, so cannot work 100% on this project because contracts are for other topics. So this is a critical point for his project, and some people have to leave this project for this reason. So, okay, thank you. Next speaker is Giuliana Fiorentino. She will talk on the stellar variability and 3D structure of the galactic spheroid.
Thank you, Amata. I'm the last, I think, speaker for, the short talks, and I will try to do my best to be very fast. Also because also because I'm one of the third group involved in the classical variable stars studies to study the star formation in the local volume, and in particular the galaxy structure and formation. And in particular, our project is about the 3D structure of the galactic spheroid. And before going a little bit into the detail of the kind of goal we hope to investigate using the huge amount of LSST data, this is just a money plot for who is studying RLR stars, for example. And this is called the Bailey diagram, so amplitude versus period, and the period distribution of the other stars. And I want to show you how, with a huge amount of data, with the sky photometric survey, we can get information concerning the structure of our and the formation of our own galaxy. So here you can see data from Ogle, from the Sagittarius galaxy, and also the LMC. And here you can see the data from Catalina survey joined to other survey that have been done in our galaxy, in our galactic halo. And from this plot, you can see that the period distribution of LMC, Sagittarius, and the halo is quite similar one each other. And these are instead the period amplitude diagrams. Okay, the peculiarity that we can see here is that there is a short period tail that is filled by our stars, which is not present in what we know in dwarf galaxies. As you know, the hierarchical scenario for the galaxy formation is predicting that the galactic halo is formed by small pieces, and these small pieces have always been thought to be the bricks, and they are used to be, as candidates, they were the dwarf spheroidal galaxies that we have around our galaxy are the best candidate to as these bricks. However, the period distribution is completely different from what we see in our galactic halo. And in particular, what they are missing is this short period tail. And this short period tail at the end is connected with the metallicity, and so with the enrichment that this kind of galaxy can have in their formation history. So using huge photometric catalogs, and in this case, these parameters, amplitude and periods, are completely independent on distance. You can give insight on which is the formation of our own galaxy. In particular, our own galactic halo cannot be formed by dwarf spheroidal satellites, at least cannot be formed by small dwarf spheroidal satellites. But instead, it can be formed by few events of accretion, like the one of the LMC or the Sagittarius galaxy. The quintuplet I'm part of is the one led by Giuseppe Bono, by Massimo D'Allora, and we are not so young unless we just have one one PhD student, that is Davide Magono, that is the real young guy. The other one are old, but we pretend to be young. I mean, LSST is giving us the ability to be young again. And we are now part of the two science collaboration. One is the Transients and Variable Stars, and the other one is Stars, Milky Way, and Local Volume. In particular, the main goal of our project are these three, like to study the different component and the transition between the different components of our own galaxy, so halo, inner and outer halo, thin disk, and the inner nuclear bulge. Then provide the metallicity gradient that are connected with the evolution of our own galaxy, and the characterization of the early phase of the galaxy evolution using, for example, stellar population traces as rare stars, as I showed you before. So, of course, Gaia will be the pathfinder for this kind of study, but given this kind of mean magnitude, of course, it will be largely improved by LSST, in particular in some region of the galaxy, like the inner bulge, the very extincted region, and also the very far away region. So everything is quite distant because of the features of the survey. So these are the reason why we are affiliated with LSST, and in particular what we are doing now is trying to interact with the LSST task force. And in the TVS, among the TVS science collaboration, there are these 5 recently activated task force, and we are inside these two. And I'm not going to explain this one because Tanya Muravevi already say something about what we are trying to do about the stellar variability in crowded field. And Massimo D'Allora will talk about that tomorrow, but just the idea is that because the bulges will be one of the most crucial places to test the pipeline, the LSST pipeline, because of the very high extinction and because of the very high crowding, we decided to select some region for which the variability is already done by OGLE, that is one of the major survey that we have so far, and with new data taken by Habisa, that is in this room, and he already did a lot of work on his data, data from DECAM, that is a similar camera to what we will have with the LSST. So in this way, joining these two data sets, we hope to say something more and to work to say something more on how to do the stellar photometry in crowded fields. But more about that tomorrow.
Okay, thank you, Juliana. Now we are already late, but if there are one or two very fast questions for the speakers, or the short talk, no? Okay. So let's thank again all the speakers of this short talk. And now we can proceed to the next speaker. The connection is on?
Yes, connection is on, radio is online.
Okay.
Someone should shift.
Yes, Raquel. She will talk on transient and variable stars science collaboration.
So someone can print.
No? Okay. Yeah? Okay. So please.
Hello.
Hello.
Hello everybody.
Hello.
So, share my screen. Let's try this. Okay. Hopefully Hello?
Hi.
You can hear me? Okay, great. There's some echo this end, so I'm a little unsure. I'll press on. Okay, so hopefully you can see my slides now.
Yes.
Terrific. Okay. Well, first of all, thank you to the organisers for inviting me to give this talk and making it possible for me to give it remotely. I'd like to give you a quick overview of the Transient and Variable Stars Science Collaboration, how it's organised, and what our current status is and our future plans. So, to introduce the overall structure quickly, Federica Bianco, who is there in the room with you, and myself co-chair the science collaboration, which is one of several in LSST, as I'm sure you know. We cover a very broad range of science, so we split that into several subgroups, 15 in total, each of which covers a specific research interest. And it's a large subgroup. We have over 250 members now from 11 countries, with Italy particularly well represented. When people join TVS, we ask them to tell us exactly what science areas they're primarily interested in. And as you can see, it splits across a wide range of science interest. Unsurprisingly, the majority of people are interested in explosive transients such as supernovae and other cosmological gravitational waves and so on. We also ask members to indicate their secondary interests because a lot of them have complementary interests. Federica has put together this marvelous interactive chart which shows the linking between our members' primary and secondary interests, which shows you the overlap between many of these research groups. And if you want to try this out for yourself, it is interactive, so you can go to our website at the bottom and have a look. Now, TVS, as you know, is very much at the heart of LSST's science goals, as we focus on particularly the transient universe. But we also focus on the study of galactic populations, the stellar populations, and essentially everything except possibly moving objects. So we cover a great range. So the science collaboration starts off with planets at the small scale, both with transiting planets and microlensing. It goes through a number of different areas of stellar pulsating stars, of magnetically active stars most recently, right through to supernovae, tidal disruption events, and right up to new galaxies, AGNs, blazars, and so on. Most recently, of course, the gravitational waves has been most active. But drawing all of these items together is a common interest in the classification and characterization of particularly transient variable types from the LSST data, but also variables of other nature, and that's a theme to which we'll recur later. So each subgroup elects a primary contact, and it's their responsibility to join us for the monthly TVS telecoms. This is because we can't really have 250 people across 11 time zones turning up all at the same time. So we ask that primary contact join us for those telecoms so that Fed and I can pass on information from the project and also to allow the subgroups the opportunity to raise any questions or concerns that they have and for the project to also hear back from them. But the job of each subgroup is to outline the kind of science that they hope to do with LSST, but also to conduct any preparatory work that is necessary ahead of time, especially important for the transient science, for which, if we don't have those preparations done in time, we may not get the full science return. And to this end, we've asked all of the subgroups to put together roadmaps. This is a plan of what work is necessary and also to describe how it's going to be implemented. So these begin with the science goals and refer to the survey strategies necessary to obtain the targets of interest and also detail any follow-up observations that may be required and drill down to the details of the technical handling of alerts, the classification of those particular target types, and what kind of infrastructure technology is going to be required in order to achieve that science. Now, I'll refer to several different aspects of the TVS website, which you can see linked at the bottom. This is very much a work in progress because we are shifting it over to a new GitHub portal at the moment, but you'll find a lot more information there. So as the subgroups put together their roadmaps, we found that the same themes were recurring time and time again. These are common challenges which affect essentially all science, particularly transient science from LSST. One of them is to optimize the survey cadence for the discovery of a wide range of different variability types. And this isn't just to refer to the main survey cadence, this is also to refer to what's called special projects, mini surveys or deep drilling fields, which can be undertaken in addition to the main survey. And this is particularly timely because we're anticipating a call from the project in the near future for proposals for these special projects. Another aspect to the work is going to be being able to identify these targets from the LSST data stream, and in particular from the real-time alerts that we'll produce. This then touches on such things as broker services, which are expected to disseminate the alerts coming from LSST, and also to provide some sort of classification service, but also in terms of making sure that those services are accessible to people and provide the information that is necessary for people to conduct follow-up observations, for instance. And touching on follow-up where necessary, this is going to involve a lot of other infrastructure, such as the accessibility of suitable telescopes, the coordination of such a large-scale follow-up campaign, given the sheer alert rate from LSST, and so that in turn brings on issues of observation scheduling. The workshop that you are at right now is one of a series that will start to tackle these issues. And I'd like to highlight another one that's coming up in the near future, this time in Pennsylvania in the United States. That will be in the 2nd to the 8th of June, and I hope many of you will be able to join us for that. So in addition to the subgroups, one thing that Federica noticed in particular was the overlap between what our science collaboration is doing and what some of the other science collaborations are doing. And she was keen to bring those people together and make sure that work is not being unnecessarily repeated. And so at the start of this year, we formed a number of task forces. These are interdisciplinary groups designed to undertake work on specific tasks of high impact. We did a survey looking for those areas where most urgent work was needed, and we came up with the following. One was to understand the needs of the community from the alert brokers. The next was to understand how crowded field photometry can be done from the LSST imaging data. There was obviously a drive towards planning for the deep drilling fields and the mini-survey proposals. And finally, we decided that a review of the available variability parameters was necessary to make sure that these targets could be properly identified. So I'll run through those task forces and their current status, bearing in mind that most of them have only just got started. The largest by far is the Deep Drilling Field and Mini-Survey Planning Task Force, which is headed up by Sarah Bonito. These have looked at a wide range of different science cases, so in many ways this is quite a challenging task they have. We've already identified at least 8 different potential science cases, and this task force will investigate the feasibility of different observing strategies and also will guide the agenda for the future workshops. The Crowded Field Photometry Task Force is chaired by Massimo Dall'Ora, and Kelly Hamilton acts as their spokesperson. They have already started a website, so you can look for more details of their work plan there. But to summarise their goals, they plan to put together a set of metrics which will determine whether or not the pipeline is successful at producing adequately precise photometry in crowded fields, and also put together a data set which could be used for testing this. That could involve, for example, data taken by the dark energy camera. They'll also look at developing different algorithms to provide suitable metrics. Now, this overlaps in many respects with the other experts within LSST as a whole, in particular those of the data management team, which is quite extensive, and the efforts of the dark energy survey team. And so the first task of this particular task force will be to contact these teams and find out where their status is. Next up is the task force for defining variability parameters. Their goal is to define the specific tools that will be necessary to fully characterize specifically pulsating variables of different types, spanning the whole of the classic instability strip. They decided to separate this into 2 sub-projects. One is the connection between the upcoming Gaia data releases and LSST itself. And the second is to focus on RL Lyrae's Cepheids and luminous variables. They are currently working to develop tools to characterize those specific types of variabilities so that they can provide a set of parameters which will be computable by, for example, some of the broker services. These will be later tested on specific data sets used for training. The last task force, I'm leading myself, and Marcus Rebus is our spokesperson. You can read in full detail on the website, but just to summarise, the goal of this particular task force is almost a sociological one. We're aware that various groups are developing broker services which will distribute the alerts coming from LSST, but also add value to them by adding information from catalogue services and by cross-matching it and attempting to identify the alerts as they come in. But many scientists we find from many different fields are either not familiar with working with alerts in that mode or haven't really thought about what it is they will need from a broker. And so what we're aiming to do with this task force is to really stimulate scientists from across LSST to really think through what it is they will need from a broker and how they expect to interact with it. And this can then be formulated into a set of scientific requirements for those teams who are doing the development. And so for this end, we've developed two questionnaires, which are designed to not just to understand the scientist needs from the broker, but at the suggestion of Marcus Rebus, and it's a good one, is to understand also what capabilities the current broker providers are expecting to be able to deliver. And so we have two questionnaires that are currently open, one for scientists and one for the teams developing brokers. And I strongly encourage you all to share these as widely as possible. We'd like feedback from you, from all astronomers, and not just those involved in LSST. So those are currently open, and they will be open until the end of April 2018. So please do click on them and answer the questions as much as possible. I'd like to wrap up with a couple of other things that are going on at the moment that touch on TVS. And this is an update courtesy of Rene and Ashish Mahabar. The first is the LSST Data Challenge. So this is a challenge that's designed to simulate classic LSST time series photometry and then challenge people to identify variability within that data set as if it were coming directly off the telescope. The purpose is to encourage the development of algorithms that will be able to handle the LSST alert stream. This has been planned for some time, and its current status is that the models are currently being validated and the data sets are in the process of being created. They hope to release the challenge soon, but you can read more about their progress on the blog, which is given at the bottom there. And finally, the Zwicky Transient Factory, although it's a completely different telescope from LSST and it's in the Northern Hemisphere, in many respects will act as a forerunner survey to LSST. It will conduct a very wide field, quite deep survey of the Northern Hemisphere sky, and it plans to issue public alerts through very similar machinery and infrastructure to LSST, with the specific goal of this being used by way of essentially a training facility. So ZTF recently started taking data, and those alerts will be made public shortly through, I believe, the Antares broker, which the full infrastructure is currently under development. And so that's given you, I hope, a quick overview of what we're doing in the Transient and Variable Stars science collaboration. We're a large team and we're growing. We're looking forward to LSST and preparing for what we see as the main challenges ahead of us. And I hope many of you will be able to join us for the workshop in June. And I'll finish there. Thank you.
Okay, thank you. And now questions?
Can you describe a little more the challenge that you are going to do?
I'm sorry, I didn't quite hear that.
I wanted you to describe, if it's possible, the challenges that you were talking about just a couple of slides before.
Ah, yes, the plastic.
Yeah, the plastic.
So as I understand it, the plastics challenge is planning to simulate a large number of light pods into which they will inject a series of different types of variability. Primarily, they'll be focusing on explosive transients, which is the people behind it are the dark energy surveys. And the goal being to stimulate, once they release the data, to stimulate people to take the data set and use it to develop classification algorithms capable of identifying and that actively identify different types of transients while they're still in progress.
Okay, thank you. Now let's thank again the Natalie. And then Massimo has some.
Just a quick announcement about the pizza. The meeting is at 7:30 at the main gate of the observatory. We have 3 cars and we have 20 persons. So probably we have to call one or at most a couple of taxis. In any case, the meeting is at the front door of the observatory at 7:30. Okay? Thank you.
Ciao, Rachel. Thank you very much. Bye bye.
Yeah, my pleasure. Thanks for having me. Bye-bye.
Grazie.